John,
Yes.
Professor Erkin John. I think we're going to start just in a couple of minutes, okay?
Yep.
So your talk will be also presented. It will be, we're going to have live stream in YouTube, okay?
Mm-hmm.
Okay, ladies and gentlemen, it's my great pleasure to introduce our first speaker today, Professor Erkin John Karimov. Professor Dr. Erkin John Karimov is a researcher specializing in partial differential equations of integer and fractional order and special functions. He is affiliated now with Ghent University, where he conducts research on direct and inverse problems. He has he has many publications in very good journals. Um, and of course, it's for us a great pleasure to have you, Professor Erkin John Karimov. Thank you very much for accepting our invitation. So the talk of Professor Karimov will be about mixed-type partial differential equations, applications in diffusion wave process. So thank you very much.
Okay. Thank you very much. The one. First of all, I would like to thank you for initiating this wonderful conference and also the ISAAC community, because this is a joint conference and it's wonderful that it is linked with the developing countries. So many young researchers will have a good opportunity to present their results and to discuss recent results on this direction. So I'm honored to be a first speaker of this conference. My talk will be devoted to the application of a partial differential equations of special type. It means the mixed type. And I will concentrate on application in diffusion wave process. But at the beginning, I will speak about some other application of a partial differential equation of mixed type. So let me start with the famous Tricomi equation, which was introduced by Francesco Tricomi in 1923. So this is the first most famous example of a mixed type equations. So you can see here when y is a positive, we will have a Laplace equation, which is an elliptic. And when y is negative, we will have a hyperbolic equation. And when y is equal to 0, we have a parabolic degeneration. So that is why this is the famous member of this class of mixed type equations. And of course, this equation arose with the application. It's linked with the sonic, subsonic, supersonic waves. So let me go to the next. So this is an application, how it was appeared and how it was interpreted. And mostly with the further modification, it was used for military purposes. That is why this topic in Soviet Union time, it was kind of a closed topic, and about 50s, who did research, who did some new results on this direction was not allowed to publish, but we get this publication later on. So for the development of this direction, we will divide like in decades, like in 40s. Some application aerodynamics was found by Frankel, and also he formulated the so-called Frankel problem, which is a generalization of the trichomy problem. And in 50s, more kind of model elliptic hyperbolic equation, which is now called as a Laurenti-Bitsaz equation, was considered, and many main initial boundary problems for this equation were considered, and more theoretical results were established in this regard. So next one on the 50s, there was also the very fundamental contribution of Kathleen Morawetz. So it is linked with the proving of non-existence of smooth transonic flows. And later on, the famous mathematician Murray Proter considered multidimensional cases, and he considered 2D trichomy and Frankel problems. And later on, after maybe 10, 20 years later, the Peter Lux and Ralph Phillips, they also considered some weak solutions to these problems, like trichomy on Frankel problems. So this was kind of also development in a more theoretical direction. So here, this is just an illustration how these mixed type equations were used in airspace problems. So here, maybe who will be interested, they can go to deep, to study how the mixed type equations can be considered as the mathematical model of this process. So here some explanations, some hints are given where the parabolic diffusion appears and when the hyperbolic equation can be used. So here in a wall process, you need to use the hyperbolic parabolic equations in a system, so we can call it as a mixed parabolic hyperbolic equations. So then so let me go to the parabolic hyperbolic type equation, which was considered, this combination was considered for the first time by Israel Gelfand in 1959. So you can I don't know is it translated into English, but probably it might be translated. But this paper is a short paper, and there was no clear explanation. But the problem was illustrated here. For example, the Gelfand described that the process of gas flow in a channel surrounded by porous medium can be modeled by mixed parabolic hyperbolic type equation, because movement of gas in a channel inside of channel will be described by hyperbolic wave equation, and in a porous medium it becomes like a diffusion. That is why it can be considered as a parabolic diffusion. So here are some interactions in this regions. So in a mathematical model, you will consider as a initial boundary problem for parabolic hyperbolic type equation. So later on, these directions were developed by mostly the Soviet mathematicians, and in particular, mathematicians from Uzbekistan, academicians Jurayev and Salahuddinov and their students. So they just started to generalize different kind of problems, and these mixed type equations also with some degeneration and some with small coefficients and small terms and etc. So these directions were developed systematically in 70s, 80s, and later on 90s. It is still ongoing results on these directions, but in the last decades, it's like not linked with a direct application. So it's just going on a pure mathematical way. And so after 2010s, this fractional calculus becomes more popular, and many equations started to be generalized in the sense of fractional derivatives. So maybe after 2 3 years, then the people who was interested with the mixed type equations, they started also to generalize these equations in a sense of fractional generalization. So they considered the time derivative, they started to consider fractional derivative. So the basic work was a fundamental result was obtained by Professor Pskou. He considered this diffusion wave equation with the famous Riemann-Leibel fractional derivative, and later on the regularized Riemann-Leibel fractional derivative, so-called the Caputo. And then, so on this direction, the people started to consider more general fractional derivatives with more parameters. So then we started to combine this fractional diffusion equation with the hyperbolic equations. So many results were obtained in a theoretical way. So this also nowadays it started linked to this kind of parabolic hyperbolic equations started to be to be applied in this tumor growth problems as well. So here also you can see some illustration where the hyperbolic equation and also the subdiffusion means that diffusion equation with a time fractional derivative can be considered as a mathematical model of tumor growth problems. So now in this talk, I will concentrate on direct and inverse problems for combination of diffusion and wave equation, the fractional generalization of these equations. And since we are using the Prabhakar fractional derivative, which has more parameters, and as a particular case, you can obtain the classical Riemann-Leibel fractional derivatives. So we need to deal with the special functions, which is one of these bivariate Mittag-Leffler type functions, and we need to deal with this function, and we need to study some properties of this function. So I will just stop on some properties and some basic steps of this investigation. So let me start with the introducing of this fractional derivative. So here, this is the regularized version of this Prabhakar fractional derivative. So it is kind of Caputo analog of this derivative. So this is like a Prabhakar fractional integral which was introduced in 1971 by Tilak Prabhakar, Indian mathematician. That's why the people started to call this integral operator as a Prabhakar fractional integral. So when you combine with the derivative, so you will get the Prabhakar fractional derivative. So this one is a regularized case. And here in the kernel, you can see this generalized Mittag-Leffler function, which has this third parameter. Some people call it as a three-parameter Mittag-Leffler function, but nowadays it's popular to call it as a Prabhakar function. So here, as you see, this fractional derivative has four parameters, and in mathematical modeling, so these parameters can be interpreted in a different way. So it allows us to consider more, maybe less assumption on a real process. So you don't need to idealize some factors, so you can control it by some additional parameters. So now, first of all, when you consider this kind of fractional derivatives, you need to consider first of all, the Cauchy problem. And then when you consider PDEs, you can deal with the solution of this Cauchy problem. But here, I would like to note the work by Ovidio Polito, which was published in 2018. And but in fact, it was uploaded to arXiv in 2013. So they introduced the regularized version of this Prabhakar fractional derivative. In fact, the original one was introduced in work of Prabhakar, so in 1971, but he didn't consider it as a separate operator, and he did not study any other properties. But the regularized version was introduced by the Ovidio and Polito. So in that paper, they considered this kind of Cauchy problem for PDE, and they used Laplace transform in time variable, and in space variable, they use a Fourier transform. So they got the explicit solution, which was presented by Prabhakar and Wright functions. So the next work is a more generalized version, like Hilfer Prabhakar. So this derivative will contains the Riemann-Liouville and the computer versions of this derivative in ones. So this operator was introduced in the work of Garra in 2014. So you see here official publication of a Caputo version was officially in 2018, but it was introduced 13. Later on, after 1 year, this official publication appeared, which generalized this Caputo and Riemann-Liouville version. But usually they refer for the Caputo version, this publication, even if it was published after 4 years of this work. So I don't know the reason why it was published later, after 5 years, but still we need to follow and cite the original work where it was introduced. So they considered this Hilfer-Prabhakar derivative in the following form, and so they also studied certain properties of this operator, and later on, based on these results, the other researchers considered some PDEs. You can see here PDE, and here in this operator, usually the fractional order refers to the parameter beta. So alpha, omega, gamma, and other parameters refers to other part, but the fractional order is linked with the parameter beta. So in this work, the author used Sumudo transform, and also they found some approximate solutions and etc. So the aim was different. Then you can see here the work which was published in 2022. And here the author considered, he found the exact solution for heat equation. I mean the generalized heat equation. So here in this space variable, you can see here the Bessel operator. So you can deal with the specific domains. And here, let me go to the next work, which is linked with me. In 2023, we considered this kind of subdiffusion equation. So we considered the regularized Prabhakar derivative, and beta is between 0 and 1. So we consider it in a rectangle, so it's a bounded domain. So we have used the method of separation of variables, and we got the solution in the explicit form, representing it by bivariate Mittag-Leffler type function. So here we need to consider ODE with the regularized Prabhakar derivative. So since we are using method of separation of variable, in time variable, we will face this kind of equation with a certain initial conditions. So if you have the solution of this, you can easily apply it later on when you consider PDEs. So this is the Cauchy problem, and this is for regularized Prabhakar derivative, and it has the following explicit form of the solution. And here you can see the bivariate Mittag-Leffler type function E2. So if you have the certain properties of this function, you can use the later on for PDEs. In fact, so this kind of problem, I mean, this kind of Cauchy problem was considered before as well by other specialists like Aran Fernandez with his co-authors. They considered this kind of Cauchy problem by other method like Mikuchinsky operational calculus. And in our case, we have used the method of integral equations. So we reduced this problem to the integral equation, and using the successive iteration method, we have found the explicit form of the solution. But the same result was found by other authors years ago, but they did not present the solution via bivariate Mittag-Leffler function. They just wrote the infinite series of Prabhakar functions. So later on, it was a problem to find an estimation for this function, and then the further results were waiting for consideration. So that is why, based on our result, we later on found this kind of integral representation of this bivariate Mittag-Leffler type function in order to get an estimate for this function. When we have an estimate of this function, so we can estimate the infinite series. These are very essential for us. Oh, I'm sorry. So it goes very fast. So, okay, so this was the integral representation of the bivariate Mittag-Leffler function. Then we need to consider this kind of expression delta k, and probably it was not the, maybe I will come back to this statement later on, because this expression This statement is very important for us to get the explicit form of to prove the uniform convergence of infinite series. So when we prove this statement, we have used certain properties of bivariate Mittag-Leffler function. This is in fact, the integral representation and also some estimation. So previous lemmas will be used to prove this statement. So next one is related with the other estimation of this E2 function. Here we try to reduce the restrictions to the parameter. We have imposed here other restriction to the parameter. Maybe you can see here, did I present? No. Initially, we got the estimation by strong restriction on the parameters. Later on, we started to avoid this restriction, and we find this kind of estimation, which is more acceptable. So our parameters in the solution will have more freedom. So then now I'm ready to present the mixed equation. So I'm trying to avoid the terminology mixed type when I consider fractional generalization, because when you generalize the diffusion parabolic equation with a fractional derivative, so you cannot call it as a parabolic equation. So it is not the parabolic type. So that is why here I started to use the terminology mixed equation, not a mixed type. So here you just substitute to instead of signum all these values. So you can see that in an upper rectangle we will have the subdiffusion equation, and in a lower rectangle here from 0 to a you will get the fractional wave equation. So here beta 1 is between 1 and 2, and beta 2 is between 0 and 1. So here, okay, so for this equation, for this mixed equation, so in a domain omega 1, we have a fractional wave equation which describes the wave process. And after some time, it means that when t is greater than a, from A to B, so this wave process becomes like a diffusion process. So it means that we are considering time from 0 to B and from 0 to A. In this period, the process is wave, and after this time, then it becomes a diffusion. When you consider the whole process, you need to deal with the mixed equations, so wave and the diffusion equation. So here the boundary conditions are given and the initial data is known. And here you need to pay attention that when you consider the fractional wave equation, you need two initial data. But here we have only one. And when you consider this combination of two equations on the line, this t equal to a, so you need to have transmitting conditions. Transmitting conditions says that this is the special derivatives, and you can call it velocity, should be equal, and also here when we consider the function itself, so we will give here the definition of the regular solution. So did I give? Yeah, definition of regular solution says that the function itself continues in the closed domain. It means we have here the second transmitting condition, which is the function itself is continuous on this line t equal to a. So we have in fact here two transmitting conditions, one initial condition and these two boundary conditions. So with this formulates the direct problem, and the inverse problem is related with finding the right-hand side. So here, if you consider direct problems, h of x is given. So source function is given. Since we are considering in a bounded time period, so the external force does not depend on time. I mean, it may depend on space. So that is why the right-hand side depends on space only. For the direct problem, this source function is given. When we consider inverse source, means that source is unknown, so we need to have additional conditions, which is we call the final time measurement. So when you consider this process, always it is possible to get the final measurement. So this is the more realistic condition. So you can get this final time measurement, and having this additional data, you can reconstruct the unknown source function as well. So this is the two direct and inverse problems. In fact, these inverse source problems will be based for consideration inverse boundary problem as well. For example, here, if you have non-zero boundary conditions, and for example, in one side you have a kind of unknown function, which can be a function of control. So in that case, you can use a certain transformation to get the unknown right-hand side. So later on, then you will consider inverse source problem for such equations. So that is why the inverse source problem is also important for the considerations. So since we are dealing with I will come back to the equation. In space, we are just using the simple operator. So instead of this operator, you can use more general operators, but you need to deal with the certain properties of this operator. So we can consider here uniformly elliptic operator. And regarding these boundary conditions, you need to have a discrete spectrum of this operator later on, which forms the kind of complete autonomous system of eigenfunctions. So you can be able to expand the unknown function on this kind of system. So here, since we are considering uxx, the simple operator, the eigenfunctions becomes like sinus. So this system forms the complete autonomous system, which means that you can expand the unknown function via these systems, where this T1k of t and T2k of t. So we are expanding with different kind of, actually, in fact, these are Fourier coefficients, but at the beginning we consider them unknown coefficients. So we need to find these unknown coefficients using the equation and imposed conditions. When you substitute these forms to the equations, in terms of time variable, you will get these two ordinary fractional order differential equations. So 17 and 18. Here 17 B1, since B1 is between 1 and 2, this is one equation when t varies between 0 and a. And the second one is almost the same form, but the B2 is between 0 and 1. So since the right-hand side is noun function, so we can represent it with the same system of functions. So hk is a Fourier coefficient, which can be found with this formula, since h of x is given, so you can be able to find hk. So when we use the solution of the Cauchy problem, we will get the following form for T1k and 2tk. So these solutions are represented by bivariate Mittag-Leffler type function. So when we later on try to prove uniform convergence of this infinite series, so we need to estimate these functions. So we have this form. So when you try to estimate, you need to estimate this bivariate metagrapher function. So we will use the previous lemmas for in this purpose. But here, when we write down the general solution of these equations 17 and 18, we have unknown coefficients A1k and A2k, and also here B1k are unknown constants, so we need to find them. So for this purpose, we will use the certain conditions. So here, let us start to use the transmitting conditions. Here, this continuity in the wall domain gives us this transmitting condition. So we need to replace t with a, so t tends to a. So from these two solutions, you will get this kind of relation. So now our B1k is linked with A1k and A2k. So this is one equation with respect to these three unknown coefficients. The next one is initial conditions. So initial conditions is linked with the fractional wave equation. The phi is a given function, so you can expand into the same series, and then the phi k will be Fourier coefficient. So phi k is known, and so if you compare with the solution, so A1k will be found easily. So A1k is a phi k, and the next transmitting conditions look like this in terms of T1k and T2k. So we need to evaluate the derivative, and we need to evaluate the regularized Prabhakar derivative from this function. So at the end, after certain evaluations, we get the second equation with respect to unknowns. So since A1k is already known as a phi k, we have the one equation which is the relation between B1k and A2k. So this is the second equation. So you can consider these two equations as a system of algebraic equations with respect to two unknowns. So when you try to solve it, so we just replace B1k with the certain properties, and when you try to find A2k, you will have this expression which we denote by delta k. And if delta k is not zero, so you can count as a main determinant of this algebraic system of algebraic equations. So the main determinant shouldn't be zero. So this leads us to impose the conditions to this. And here we proved in lemma 3 that when k goes to infinity, so this expression is not zero, which states that you know that k is starts from 1 to infinity. So if you prove that when k goes to infinity, this expression is not zero, it means that it might be zero only in a countable number of k's, which is acceptable for solving this, to finding this unknown coefficient. So when it's zero, okay, so we cannot be able to find the coefficients. But in that case also, there is a possibility to find the solutions. There should be some conditions on the right-hand side, and there is a special link, but we will not consider this case. So we say that if this expression is not zero, then we could be able to find unknown coefficients. So now I will not formulate the statement regarding this direct problem. So here I would like to formulate the results on inverse source problem, because for consideration of inverse source problem, we will base on the solution of direct problem. So here, if you remember, the inverse problem was just the right-hand side is unknown, and we need to impose the additional condition in final measurement time. So we will use this condition. So it appears like this, the final measurement condition. So we substitute our solutions to these additional conditions, and from 25 means that from this equality we could be able to find HK. In order to find the HK, here we need to divide by this expression, and we need to make sure that this expression is not zero. Here, for the certain parameters, I mean here, if gamma 2 equal to beta 2 and alpha equal to 1, this denominator is not zero. So that one we have to prove. So we prove it beforehand, and we make sure that this is not zero and for any values of these parameters and any values of k. So that is why this restriction appears for the parameters, and we could be able to find all unknown coefficients. So here we just, in order to not write down the bulky expressions, we just introduce some notations. These expressions we denote by N1K. So then to find B1K, we have this kind of equation. And another notation is also needed to just simplify the equation. So we introduce this N2K and N3K, and we will have another equation. So again, we need to introduce N4K. So finally we got the third equation. So if we collect, we have the unknown coefficients B1K, A2K, and HK, and we have three equations. So we need to solve this system of algebraic equations. And here also as a main determinant appears this kind of expression. So N1K, N2K, N3K, and this kind of combination. So that is why we just introduced this notation. So this delta K bar is different than the previous delta K, but here I just would like to rewrite in clear form how this delta K bar appears. But here you can see this bivariate Metcalfe function, and also somewhere you find the multiplication product of these two functions, etc. So here, very bulky expression of this, but the key part is we need to prove this lemma, which says that when k goes to infinity, this delta K bar is not equal to zero, which provides us to which allows us to say that this delta K bar will be zero only for countable number of k's, which is also the acceptable solvability conditions to the problem. So now we will present our main result. We assume that this delta K bar is not zero, and also we impose the restrictions to the parameter. These two conditions were necessary for proving that in denominator the expression is not zero, and also for the given data, all these conditions we need when we prove the uniform convergence of this infinite series. And here you can see we need to even the ninth derivative of the given data. So eighth derivative should be continuous, and ninth derivative should be square integrable function. And also at the end of this boundary, so this derivative should satisfy certain conditions. And in fact, for the inverse problem, this regularity is usual. So for inverse problems, we need to increase the regularity for the given data. And for the direct problem, we can reduce these regularity conditions. And by this statement, we can prove the uniform convergence of infinite series, and we got an explicit solution, and representing by bivariate Mittag-Leffler function. So this explicit solution allows us to consider numerical part as well, because since you have the infinite series also inside the given functions, special functions, so you can easily go to the numerical part and get some numerical data, numerical graphs to for evaluation. So probably for engineers, this is most important part. And here these results were based on the works with my PhD students, Muzaffar Toshpolatov. And here we have 3 published papers. So these 2 papers already published. The second one is online, they published it online. Probably soon it will be linked with a certain issue. And the first one is accepted to this journal and will appear soon. So but we have further results on this combination, because we have considered the other versions, like wave equations. The wave process after some time becomes a diffusion, and then again becomes a wave equation. So you need to consider the combination of wave, diffusion, wave. So for this problem as well, so here, yeah. Number 3 is related to this combination. So I didn't present here because it is a bit, it has a bit bulky expressions and etc. But it is also the interesting problem. And yeah, probably I'm almost finished. So here just the last slide is link it with an acknowledgement. So thank you very much and welcome to Uzbekistan. You can consider as a touristic destination.
Okay, Professor Erkin John Karimov, thank you very much for this very nice plenary talk. I think it was very good, especially it was very inspiring, I think, for young mathematicians.
Thank you.
So now I think we are open for questions. If you want to ask some question to Professor Karimov, please raise your hand. Please raise your hand and we will be able to unmute maybe yourself. I think at this moment also anyone that wants to make a question can do it, can unmute yourself and just proceed. So it's very nice because we see 47 participants in your talk. I think it was a wonderful
No, I'm
participation.
open when they can contact me directly. Later on, we can have a private discussion. So
Okay, very good. So for the participants, if you want to write an email to Professor Karimov, maybe in a more close discussion, he's open to do that. Maybe I have a question, Erkin John. In these slides, right, where you show where you show it was summarizing the different models, right? The
yeah.
parabolic one, the hyperbolic one. Could you please go to that slide? Sorry that I don't. It was close at the very beginning, right?
You mean the illustrations?
Right, in the illustration.
Okay. So let me go. Maybe this?
Maybe, maybe this one.
Yeah.
Right. Do you have cases, for instance, the one in the middle is hyperbolic. Do you have no? Do you have sorry, someone to the
Yeah,
participants, please take care of your microphone, I think.
I can unmute. I can mute. So now you can
Okay.
continue.
Um, do you have a specific application in the case where, let's say, you have non-constant coefficient in the right-hand side of the wave equation? I mean,
Uh, yes. So if you mean the source function may depend on time as well. So
right.
for direct problem, even for the inverse problem, it is not the big problem. So if we use the method of separation of variables, so we can consider the case when the time dependent on source function depend on time and space. So uh, this is also uh, can be considered, and there will be no such a difficult problem. Only in the expressions you will see the right hand side and also the bivariate Metcalfe functions. This kind of combination will be added. So this is possible to consider.
Thank you. And maybe continuing that discussion, because as soon as I know, when one has variable coefficient terms, right? One use Fourier integral operators and this kind of
Yeah.
tools,
For
right?
the
But in your case, what do you use? What changed when you were using that
For
analysis?
the variable coefficients, if it's linked with the space, so somehow you can consider this kind of, for example, the Bessel operator or specific variable coefficients. But if it depends on time, this is a bit challenging. So you need to deal with the fractional differential equations with the variable coefficients, and in most cases you don't have an explicit solution. So we have a specific cases where we have a explicit solution like a Kilbas-Saigo function, and you have the estimation for this solution, and you can deal with this. And also there are works by Suragan and Restrepo where they considered these variable coefficients, but they didn't give an explicit form of the solution. They just rewrite with the combination of the integral differential operators. And we couldn't be able to use this. They gave certain examples when these coefficients have the certain form, and they can consider the explicit form. Then you can consider the different kind of problems when you need to use the estimations.
Thank you very much. So, are there questions for Professor Erkin John Karimov? So there is a question in the chat. In the
Uh,
chat,
how can I see the question?
Melong Melong asked about the importance of the Pratt-Hakar fractional
Uh-huh.
derivative. Mhm.
Okay. So as I mentioned, the Prabhakar fractional derivative has more parameters. Uh, for example, here in the kernel, uh, in the case of Riemann-Liouville fractional derivative, we don't have this. It means that you lose the parameters gamma, alpha, and delta. And in fact, if you deal with the memory effect, usually the fractional derivatives is linked with the memory effect. So these additional coefficients will allow us to consider some cases where we need to omit for the classical case of Riemann-Liouville fractional derivatives. And this we can call it this Prabhakar fractional derivative, or maybe this kind of generalization, we can consider it as a multi-parameter integral differential operator. So this specific Prabhakar fractional derivative uh, allows us to find an explicit form. Someone can consider more general, for example, instead of this Prabhakar function, someone can put the hypergeometric function, or maybe generalization of hypergeometric function. And you may have more parameters, but you will face a problem to find an explicit solution of this operator. But in this case, the Prabhakar fractional derivative was enough good to have more parameters and also allows us to find an explicit form of the solution. But if you are interested in specific properties of this advantage of this Prabhakar fractional derivative, you can go to the work of Tarasov, where he considered certain properties and also applied to the economical problems, etc., in dynamics. So maybe you can find more detailed information in Tarasov's work.
Okay, thank you very much. I think still we have time for a couple of questions. Are there questions for Professor Erkinjon? You can write the question in the chat, or you can unmute yourself. Maybe, Professor Erkinjon, could you please let us know about open problems in this topic? I think you emphasize at the end, but maybe for young people,
Yeah,
would be nice.
for example, this is the open problem when we consider in groups.
Oh,
In groups, we still did not consider such a problems. So we are considering here in a specific domains, like a rectangle and maybe like in a cylindrical domains. But if you allow in a space this specific operators, when you cannot use this method of separation or in other kind of Green's function, etc. So then these questions are still open. And also as we already mentioned, the equations with variable coefficients, still open question. So here for the Prabhakar, if we have even this t in power, some power function coefficient, it is still open question. So it will be interesting to see the explicit form of the solution with such a variable coefficient equation involving the Prabhakar fractional derivative.
thank you. And maybe last thing, before you stop sharing, if you can share with us the photo that you show at the end of Uzbekistan, because
This is in fact this is the AI generated photo, but in reality you can find more beautiful places.
right,
More beautiful places. So I was a bit shy to share more pictures of Uzbekistan here,
right.
but I hope you will find it interesting place
So
to visit.
thank you very much for this very nice invitation for us, on behalf of ICMAM Latin America. We appreciate that you accept our invitation and also to have this version of the ISAAC-ICMAM conference also be supported by the Romanovsky Institute of Mathematics. So it has been very nice to have you with this very nice talk. Thank you very much, Professor Karimov.
Thank you very much, you as well.
Okay, very good.
I'll stop sharing now.
Okay, thank you very much. So many reactions. People are happy with your talk. I invite now then our next speaker, Professor Doniyor Usmonov and Manuel Martinez, who will chair the session.
I am here. Hello,
Oh, okay.
Professor Duan Cardona.
Hello. So, Frederick is the chair or Manuel?
Yes, yeah, it's Frederick.
It's Frederick. Oh, hi, Frederick. So, very good.
Okay.
So, I will pass then chairing
Okay.
to
So,
Frederick.
so our next speaker is Osman Donio. So for the meantime, I would like you to share your screen with us before we proceed with the introduction.
Is it visible?
Yes, please, can you make it a little big?
Okay. Hello, everyone. I am
Oh,
Usman Faneor. I am from Fergana State University. I talk direct and inverse problem for Barenboim Chiltov-Kochina type equation with regularized Papagar fractional derivative. It is known the theory of differential equation has long and rich history until the last quarter of the 20th century. This theory primarily dealt with integer order differential equation, with the development of the fractional calculus starting from the late 20th century. Researchers began study differential equation contrasting fractional derivative. Today, numbers have been published examination in initial boundary of the spectral problem for differential equation, ordinal and partial differential equation involving fractional order with modification. The development of the field has been the books six Nachschub fractional calculus and Samko Kilbas Marchev and Kilbas Rivastava Trujillo. The main process and the equation of the theory of the non-stationary filtration in fractional pore formulation are formulated in the work of Barenboim, Chiltov, and Kochina. These articles and maybe afters all articles. In 19 article, scientific conditions are found of the inequality stability of the Cauchy problem for Barenboim-Chiltov-Kochina equation. This one in 2020 equation 1 in study of abstract initial boundary problem in Banach space Umarov by Umarov. In 2022, Professor Ashurov and Waiswa study the following non-local problem for Rayleigh-Stokes equation in Hilbert space. This problem and Professor Ashurov and Mukhudinova Sabrumarov this equation study inverse problem. Okay, next section primitive Mittag-Leffler time function. This function, Mittag-Leffler time function or Prabhakar function, two parameters. This here alpha, beta, gamma in complex number and real alpha positive and real beta positive. And Pochhammer stimulus by formula this. For gamma equal 1, we write two parameter Mittag-Leffler function this. If for gamma and beta equal 1, this function classic Mittag-Leffler function. If alpha equal 1, beta equal 1, gamma equal 1 is exponential function. The property Mittag-Leffler type function, this formula, the derived Mittag-Leffler function E2 by formula 2 have been studied in Garg, Manahart, Erkincan Karimov, Nias Tormugambedov. The function converged for all x, y, if
Why? Y.
the three variable Mittag-Leffler function f2a in type series converged for x, y, z in complex number if delta 1, delta 2, and delta 3 positive number. Here delta 1, delta 2, delta 3. For function 2, the following differential and integration formulae are valid. This formula 4 and 5. Okay. Next section, Riemann-Liouville and Prabhakar integral differential equation. These 6 formulae, Riemann-Liouville fractional integral operator and Riemann-Liouville fractional derivative operator and this fractional integral operator Prabhakar in the kernel Prabhakar function or 3-parameter Mittag-Leffler function. This Riemann-Liouville Prabhakar derivative equation, Riemann-Liouville Prabhakar derivative operators, and Riemann-Liouville regularized Riemann-Liouville fractional derivative or Caputo type fractional derivative. Prabhakar operator, the semi-group property with reception parameter theta, theta 2, beta, beta 2, gamma, gamma 2. Which one formalizes the theorem combination derivative and integral operators this formula if beta in 0, 1, then we obtain formula 11. And Prabhakar derivative Riemann-Liouville type and regularized Prabhakar fractional derivative, the following relation, these formulas, and beta 0 and 1, so that m equal 1, we obtain formula 12. Okay, next section, main relays. This let us consider following fractional variable Ziltov-Kochina type equation in domain rectangle. Here, f given function, we got for alpha, beta, gamma at all in real number, alpha positive number, beta in 0 and 1. We set at beta equal 1, delta equal 0, equation written becomes classic pseudo-parabolic equation with this. We formulated Gursa type problem for equation and regularized conditionals and initial condition, boundary condition, and here tau phi1, phi2 given function such that tau 0, phi1 and tau derivative 0, phi2, 0. Integration equation twice order 0 and x, we obtain equation this. Here E2 Riemann level fractional derivative of order 2. We applied the operator Krapka fractional integration. The condition equality 11, which is this, and we obtain second kind of Volterra integral equation of the from this. The solve equation for t, we applied method of Simpson approximations. This U0, this and UM. Okay. Using formula 8 and 10, we find that UM, we obtain this formula. The function 70 can be written as following this. If the limit m infinity exceeds uniform in t equals the limited function a solution integral equation for t, taking the limits as around infinity in U0, we obtain solution of the find the equation from 18. Besetting n plus n equal key here we can of the order summation according of the formula. This by calculate articles using formula 18, the function 90 can be written of the following this. If we introduce the notion, this formula, then the function 20 can be written as following this. Okay. Some conclusion we obtain the following result when b positive number. This formula, long formula. And if beta non-positive number, the function hyperbolic cosinus and hyperbolic sinus solution are replaced by cosinus function and sinus function. Theorem 2.1, if tau 0 and phi 1 0 and tau derivative 0 and phi 0 and function in this class, then the solution of the problem G exclamation and inequality of determined by formula 22. Okay, next section, inverse problem. We consider an inverse source problem for the equation 24 in domain rectangle. Here, ft unknown function. Problem I, this equation, regular initial condition, boundary condition, and overdetermination condition. Here, tau phi 1, phi 2, omega t, given function. First, let us write in the solution 22 in the form this formula. At x equal x0 in the x0 in the 25, we get this equation. Okay. The relation equation 26 will be right in the similarity this equation, Walter type equation, and first kind Vt by this formulate. Okay, then we apply operator integral Riemann-Liouville integral order 1 minus beta side of the last equation. Okay, the charging order of the integration we get this equation. And inner integral using series of the function f2 one can deduces. And the relation equation will be separated as this equation, where f02 generalized hypergeometric functions. Now we take the derivative with respect to t. We obtain following second kind Walter integral equation 28. Okay. Theorem 4. If tau 0 phi 1 0 tau derivative and phi 2 0, then solution of the problem I estimate is inequality. Thank you very much for your attention. I don't know here.
Hello. Yeah, we are sorry for this technical issue. So what I was saying was that um, Dr. Donima, thank you very much for such a nice presentation. So it's time for question. If you have any question, you can kindly unmute yourself or use the chat box. So it's time for questions. Please, Dr. Daniel, please can you share your screen once more? So please, we are taking questions from participants. Please, Dr. Osnov, can you share your screen once more? Okay, thank you. I think Doctor has made his internet connection, so we may proceed.
Okay. Okay, yes. Just let's wait a couple of minutes to see if we can have again Professor Usmanov with us. Is Professor Donillor Usmanov in the Zoom, in the meeting? Okay, I think Professor Usmanov has a problem of connection, right? Okay. Okay, so uh, thank you to all the participants for being here. Our next talk will be at 16, so in almost around 40 minutes. So please join us in the next talk of Professor Claudia Gareto, actually from Queen Mary University of London. So we are going to resume at 16 in Central European Summer Time. Hi everyone. I think we have enough time, maybe to know each other here. I would like maybe to see the people that are joining us today, because our next talk is in half an hour. So, Marcial, how are you?
I'm fine, and you, Professor?
I'm very happy to have you connected. Where are you from, Marcial?
Uh, I'm from Cameroon,
Cameroon. Oh, wow. It's very nice then to have participants from Cameroon.
in Central Africa.
We have also Professor Igor Trushin with us from Japan, I think.
Which professor?
Igor Trushin from Japan.
Tushin, no. I'm happy to be there. I'm doing numerical analysis of PD.
Very good. Numerical analysis and partial differential equations, you say?
Yes, our partial differential equation. With finite element method. I'm doing it on manifold.
Very good.
Yes.
So
We apply the surface finite element method. That the finite element method applied on surface, called
Very good.
surface finite element method.
Thank you for being here. Manuel, how are you?
Hi, a pleasure to be here.
Yes. Maybe you can present yourself to the participants.
Sure thing. Good morning or afternoon to everyone. My name is Manuel Martinez Flores. I'm from Guatemala in Central America. I have been working with Professor Duan for almost 2 years now. I did my undergraduate thesis under his supervision. I am part of the young researchers of ICMAM with some other students. Some of them are here joining us. Now I have helped the scientific committee and the organizing committee in several conferences, including this one. And it's a pleasure to have each and every one of you here. Thank you for joining us.
Thank you very much, Manuel, from Guatemala. So it's very interesting. Maybe if the participants want, you can also share the place or the country where you are following us in the chat. I saw also Melong from Cameroon also. Melong. We thank to the participants. We have somehow Manonde from South Africa. Manonde, who actually will join our research group in analysis and partial differential equations in developing countries, Manonde. from South Africa, from African Institute of Mathematical Science. Vanessa Hurtado from Colombia. Welcome. Semever from Brazil. Cavet from Ukraine. Remember that if you want to present yourself, just unmute the microphone and let us know who you are and from which country you are following us. Johar Abbas from Pakistan. Faisal Akoud from Morocco, but now working in Italy. Gaetano Siciliano from Italy. Actually, he has been very close to the ICMAM conferences and also with our editorial project. Thank you, Gaetano. Kevin Esmeral from Colombia, from Universidad de Caldas. Welcome, Kevin. Remember, you can write in the chat who you are and the country from which you are following us. Maybe I will use this time maybe to share with the participants more information about ICMAM Latin America. But first, okay, let me read. Also, Rocibel Pacheco, Professor Rocibel Pacheco, who actually is the president of the Sociedad Matemática de Honduras. Johar Bass is recommending us to give certificates. We are going to make certificates for all of the participants, of course. Mohamed from Morocco, making a postdoc in France. Congratulations. Luis Lozano from Colombia, doing a postdoc in Brazil. Maria Paulina from Colombia, working in, student in Politécnico de Colombia. Alexandra from Belgium. She's happy to follow our event. Who wants to share who you are and the country from which you are following us? Just write it in the chat. Jerry Ossi from Ghana, you are welcome. Thank you for joining our conference. Juan Pablo Lopez from Colombia. In which area are you working, Juan Pablo? Analysis and discrete mathematics. Very good, congratulations. Very good. I would like to remember to all the participants, particularly to the young mathematicians that are here, that are following our conference, that at ICMA Latin America we have different open calls, right? If you are a young mathematician and you want to publish your articles or just to announce your results, you can usually just visit our website and see different open calls that we have for different areas of mathematics. For instance, if you are a specialist in differential geometry or you are working in differential geometry, there is an open call in this area. Actually, you can contact the editor, Brian Grajales. Here is the email that we do with respect to this book series is to publish short papers, right? You can present brief communications, you can present open problems, discussion surveys, or just announce your results in mathematics. Usually, these kind of publications follow the evaluation of an standard good quality scientific journal. So you are welcome to submit your works also in analysis and partial differential equations, in algebra, in logic, right? Also, if at some point you are interested in organizing a virtual conference with ICMA Latin America, we have a permanent open call to do that. Just,
Genial.
muy bien, también podemos hablar en español. We can talk in Spanish, we can talk in English, in the language that you wish before of the plenary session. So, profesora Rocibel Pacheco, tú estás con nosotros, ¿verdad?
Sí, sí estoy.
Muy
Estaba poniendo que me interesa mucho la dinámica de fluidos y los procesos estocásticos discretos.
Muy bien, muchas gracias. Thank you very much for sharing with us your topic. Muchas gracias por compartir con nosotros tu área. Your hard works in fluid mechanics, he says. Congratulations. Hi, Professor Claudia Gareto. How are you? It's allowed to you to unmute, you can unmute yourself? Or it's not possible?
Oh, now I manage. Hi, hello everyone. Hi, Duan.
Hi.
I
How are you?
managed to unmute myself.
Thank you. How is the weather in London?
Good. The weather is very gray. It's cold. It's raining. It's the usual, basically.
Very nice. Thank you very much for accepting our invitation.
My pleasure. Thank you for inviting me.
I think maybe we can just
Shall
prove
I
if you can
try?
share your
Yeah,
screen.
to share, yeah, so that we see if it works. I believe this one. Let's see. Can you see it? Let me make it bigger. Okay, so how do I do? Oh, no. Sorry. Okay. Is it big enough for you or not? Is it full screen or not? Not really.
It's not full screen. It's not full screen. It's visible for us, but not full screen yet.
Okay, so let me then try again because I believe it was not. Let me make it full screen.
Don't worry, we have time.
Okay, so now maybe I try again. Where is it? Share. I'm gonna share probably my whole screen. In this way, it's easier. Okay, let me share the screen. And then I can do this. Now you see it better, right?
Yes.
Okay, now it's better. Good.
Thank you very much. I think we have 10 minutes to start your talk, but then let me just introduce Manuel Martinez. Manuel Martinez from Guatemala, a young mathematician who actually is working in pseudo differential operators. So it's
Fantastic.
very close to our topic. I will say our topic also.
Indeed.
Thank you very much, Duan. Dear Professor Claudia, thank you for joining us here. I'll be presenting you today. Thank you for accepting our invitation. We'll begin in 10 minutes. Thank you.
Thank you.
Wow, even it's very early in Latin America, but we have good participation from there. 42 participants at this moment, so
Oh,
very nice.
fantastic.
Fantastic, yes.
And I believe last week a colleague of mine gave a talk as well, right? Federico Ardila told me that he gave a talk last week. He told me to say hello to you, Turan. I saw him this morning.
Thank you. Thank you. Please pass my greetings to Federico,
I will.
actually. Actually, it was in the Latin American Seminar of Mathematics, where Manuel also is organizer. So we have time to make a coffee.
I was just checking how it works with the setup is a bit strange. Let me see. Just checking that actually. Oh, yes, it moves. Okay, good. Right.
Okay, good morning or afternoon to every and each one of the participants. Thank you very much for joining us today. Right now we have the presentation from Professor Claudia Gareto, who is a professor in the School of Mathematics at Queen Mary University of London. Thank you very much, Professor, for accepting our invitation. We are very honored to have you with us today. She's gonna present us about Schrödinger type equations with singular coefficients. And Professor, feel free to use the time. It is all yours. Thank you.
Thank you. Thank you very much for inviting me. I'm actually quite impressed by the activities that you organize, the many workshops, your presence online. So well done for all of your work. All right, so today's presentation is about some recent work that I have done in collaboration with Alexander Arias Jr. from São Paulo University, Alessia Scanelli from Ferrara University, and Marco Capiello from Torino University. And this is a work on Schrödinger type equations with singular coefficients. All right, so let me see why I cannot change the page. Come on. Oh, oopsie. Strange that Okay, all right, found the way. Okay, so this is the plan of the talk. I will start with some introduction, why we are interested in this problem. Then I will explain you how in this theory we handle singular coefficients, and in particular, I will introduce the concept of very weak solution that might be known to some of you in the audience. The majority of the talk will be focused on distributions with compact support, but then in the very last few slides, I will deal with the case of general temporal distributions in S prime. All right, so let's start. This is our setup. This is the kind of Cauchy problem that we want to deal with. So I have written it here in generality. S is a Schrödinger type operator of this type. I want to be general, which means that I'm taking here a coefficient, a variable coefficient depending on time. I also have lower order terms of order 1, and then I have a potential, so a lower order term of order 0. And as usual, with capital D, I mean the derivative, where in front I have the minus I, so the minus the imaginary unit. So if I look at the operator here written on this slide, actually I can see it as a P evolution operator. So with P evolution operator, where P is a positive integer, I mean an operator of this type, where AP is a differential operator of order P, and I'm taking a real value symbol. And there is a well-established theory of P evolution operators. And if I take P equal to 2, then I will have the operator S, which is written here. But when P is equal to 1, then I have a strict hyperbolic operator. When P is 3, I have a KdV operator and so on. And Marco, Alessia, and also Alexander have written several papers on P evolution operators for P up to 3. So let's say that there are many results for P equal to 2 and P equal to 3, but it's difficult to develop a general theory. And again, all the results available in the literature, they usually assume a certain level of regularity. And I will tell you more in a moment. All right, so, oops, again, here we go. Okay, so what do we know about this problem? I will try to summarize many results, so probably I will forget some of the references, so apologies in advance. Let's say that when we work under assumptions of regularity, which means that we have at least continuity in time and we have smoothness in X. Actually, we request even more. So when we have smoothness in X and also boundedness in the coefficients and for all the derivatives, so B infinity behavior, then under this assumption of regularity, the problem is very well understood, which basically means that we get well-posedness of the Cauchy problem in Sobolev spaces. So when the coefficients Cj's are real value, then the operator will define a self-adjoint operator. So, and again, we have a very well-established classical theory. So again, there are no issues with the well-posedness of the Cauchy problem. The situation is more complicated when these lower terms here of order 1 are not real valued. So if we have an imaginary part which is not vanishing. So in this case, there have been different papers. So for instance, there is this very famous result by Iquinose in 1984, where it proves that when we take the classical Schrödinger operator, so when we take the coefficients A here equal to 1, so Iquinose proved a necessary condition for the well-posedness in H infinity of the corresponding Cauchy problem. And this condition is a sort of an integrable condition, if you want. So it's a bound of this type, which is of a logarithmic type. And again, it's a condition on the imaginary part of the coefficient Cj. So Iquinose conditions becomes also sufficient, but only when the space dimension is equal to 1. So it is common in this kind of analysis to have results that hold in space dimension 1, and somehow the proof is not too complicated in that case, okay? But when you try to work out a general proof in Rn, things become more complicated and some technical assumptions are needed. For instance, some assumptions on the behavior at infinity of these lower order terms coefficients, some decay, and so on. And I'm going to mention here a result by Kajitani and Baba in 95. So if we assume that the coefficient A is positive, non-vanishing, and real valued, and continuous, and then if we have a certain decay at infinity of Cj and C0, then we can prove well-posedness, and the well-posedness in the corresponding spaces that we are using is related with the rate of decay here. So if sigma is bigger than 1, then we can prove HM well-posedness for every Sobolev order M. If sigma is equal to 1, we will prove well-posedness in H infinity, which is the intersection of all the Sobolev spaces. And when sigma is between 0 and 1, we will not prove Sobolev well-posedness, but we will prove Gevrey well-posedness, and the Gevrey order is related to sigma in this way. So this is a result which is very complete, very interesting, and that we are going to take into consideration, in particular when we will want to deal with singular coefficients, and we will start the very weak solution machinery. Alexander, Alessia, and Marco have also studied well-posedness of this Cauchy problem, but in a slightly different functional analytic context. They've used Gelfand-Shilov spaces, and again, they have assumed specific hypotheses on the lower terms in order to prove well-posedness in Gelfand-Shilov spaces. So what happens when the coefficients are less than continuous? This is quite a typical question in my kind of research, because I've done a lot of work on equations, PDEs, so in particular hyperbolic PDEs in presence of discontinuous coefficients. And usually when I ask this question, the answer is that there isn't much known when coefficients are not continuous. So there has been some work also from mathematicians actually present in this call when we have singular potential. So basically when the terms C0 is non-continuous, and usually these papers assume that C0 is in LP spaces or in modulation spaces. But in general, if we want really to be as general as possible, and therefore also to assume that the the coefficients in the principal part and in the first order part are non-continuous, the situation is very unclear. And for the sake of this talk, and to make things a little bit simpler, I will work on this toy model, if you want, where I've decided that the coefficients that depend on time and space are actually the product of a coefficient in time with a coefficient in space only. And I want to be as general as possible, which means that I drop completely the assumption of continuity. So the coefficients, the principal part A, is positive and bounded, okay? Never vanishing, non-continuous. And here in the first order terms and also in the zero order terms, I am working with distributions with compact support. So AJ and A0 are distribution with compact support. BJs and B0 will be some temporal distribution that I will specify in a moment. So clearly, when I work in this context, right, and I drop completely the assumption of regularity, I create a lot of problems, right? So I create a lot of issues because it does not even make sense then to write S applied to a distribution U, okay? And this is related to the fact that I might need to multiply two distributions. And as you all know, this is not in general possible. Okay, so how do we handle singular coefficients? Well, the idea is very simple, and probably it is known to the people in the audience working in the very weak solution context. It's an idea which is very old, which is basically the idea of regularizing the coefficients via convolution with a modifier. And this means to replace S with a family of regularized operators. What does it mean, regularize? It means that in the family of operator S epsilon, which will converge to S when epsilon tends to 0, the coefficients have been regularized, and therefore they are very nice. They are smooth functions. So if I do this regularization, so let's imagine for a moment that we are skipping like all the technical part, all the details. So we have done the regularization, and we have done it everywhere, which means not only at the level of the operators, but also on the right-hand side and as well on the initial data. I will end up with a problem that for fixed epsilon is a very nice problem, because I have all the regularity that I needed, probably even more. So now the point is we will be able to solve this Cauchy problem because there is a classical theory which has been developed in detail. So for instance, we will be able to use result as Kajitani, Baba, Ikinosa, and so on. So what I get is a net of solution U epsilon. But what I really need to do now is to investigate the properties of this U epsilon. In particular, I need to estimate this U epsilon, and I need to end up with a nice behavior with respect to the parameter. So if I manage to get so, then I have generated what I call a very weak solution. So, but the key in all of this is actually to find the right regularization method, which means to find the right way to regularize all of these coefficients in such a way that when I work now at the level of the S epsilon problem, I am able to apply the well-Posner results that come from the classical theory. So for instance, the result of Kajitani and Baba. Okay, so in the next few slides, I will go through the different ways of regularizing the coefficients. So it could happen, it easily happens actually, that I cannot use the same regularizing method for all the coefficients. So I might need to act in a certain way when I regularize A of t, and maybe use slightly different regularizing methods on the lower order terms. But let's start from the beginning. Okay, so here we go. So first of all, the standard modifier is a positive function in the Schwarz class, okay, with integral 1, and I define phi epsilon in this way. So this is really standard in distribution theory. What we know is that when I take the limit, when epsilon tends to 0 in the space of distribution, I get delta. All right, so let's take the coefficients in the principal part that we said to be bounded only, so non-continuous, bounded, and positive. So I have a compact support, so I'm gonna basically extend the coefficient so that I can do the convolution, and then I'm gonna restrict again on the interval 0t. So now, it is quite crucial that I preserve the good properties that the coefficient A of t had at the beginning. So in the statement of my problem, I had assumed that this coefficient is bounded, but it's also bounded from below, so it's never 0. So I want to be sure that when I do the convolution, I'm still getting this kind of an estimate from above and from below. Maybe I will need to change the constant a little bit, but I want that this estimate is valid independently of epsilon. And that's exactly what I can get via regularization with convolution with a modifier. So I might maybe need to work on a slightly smaller interval in epsilon, but this is not a problem, because at the end of the day, I'm just interested in what is happening when epsilon tends to 0, so when epsilon is small. Okay, so this is the first regularization of the principal part, and it is done in the right way because I preserve the kind of property of boundedness of the coefficients that I wanted. It is really crucial in our proof that here we don't have any blow up with respect to epsilon. So I don't want to have an epsilon -1 here because it will break everything. So I really need this kind of a behavior. Okay, so now we can pass to the other coefficients. And again, so I am gonna regularize in time, because remember that the AJs are the coefficients in time. And here I just need a standard modifier, so I need a rapidly decreasing function with integral 1, okay? Now, if AJ is a temporal distribution, then simply making use of the theory of distribution, so making use of the structure of the distribution, I get an estimate of this type. This N0 here depends on the order of the distribution, so depend on the structure of the distribution, okay? So I will have a blow up here in epsilon. This is something that cannot be avoided, and it's typical of the structure of the coefficient, but I can compute it very precisely. So I'm able actually to do very precise estimates, and in this kind of analysis, it is really important to do precise estimates. So it is not enough to say here, okay, we have a certain constant depending on epsilon. No, so I need to write precisely how this constant is depending on the regularization method. Okay, so this is how we regularize the coefficients of order 1 in time. Now we can move to the part in X. And this is where we realized that we needed somehow to select a certain specific class of temporal distributions. So I'm going to introduce it, and then I'm going to explain you why actually we needed them. Okay, we have introduced some intermediate classes between distributions with compact support and temporal distributions. And these classes are easy to understand if we work at the level of the Fourier transform. So basically, we are requesting that up to a certain order of derivatives, right? So up to order I, the Fourier transform has a polynomial, has a certain polynomial behavior, right? So has a certain growth of order p beta. And here in the notation, you see the I, and I means the number of derivatives that we are taking. So why we have decided to introduce these spaces? Because if we now look at the regularization, right, so the convolution via the convolution via the mollifier, and we do these computations here. So basically, we are thinking about decay at infinity. So we are basically taking here in front some powers of x. Then we can do the computations, right? So here we will make use of this polynomial estimate, which means that we can get integrability. So in other words, it means that we are gonna get estimates of this type. So we are gonna get estimates in epsilon that are the typical ones that we want to get. So the so-called moderate estimates, because we have this negative power in epsilon. But we are gonna also get a certain decay at infinity. So this is particularly important because when we fix epsilon and we look at the regularized problem, we want to be sure that we are under the assumption of the classical theory to get Sobolev well-posedness. So we want to be under the assumption of the result of Kajitani and Baba. And if you remember, that result that I mentioned at the beginning of my talk requires a certain decay at infinity of the lower order terms. Actually, for the kind of result that we wanted to obtain, it is enough to have decay here of order -2. So actually, we are choosing Bj in this space. And for B0, we don't actually need decay, so it will be enough to take B0 in the space H minus infinity 0. Okay? All right, so summarizing, we have in time a distributional behavior, so distribution with compact support. In X, again, we can use distributional coefficients, but we need to choose them in a sort of more accurate way so that when we do the regularization via convolution, we get a certain decay at infinity. Now, summarizing, we are going to choose F in this space, so continuous in time and with this temperate behavior in X. We are going to choose the initial data as well in this space. This means that once we do the regularization via convolution, we have the decay, a decay of order -n -1. And the power here in epsilon will depend on the structure of the coefficients. And by making use of all of these assumptions and regularization methods, we make sure that once we have the problem as epsilon, then it is well posed in Sobolev spaces. So we regularize S, we get S epsilon, we regularize the right-hand side and the initial data, and we arrive at this Cauchy problem here. On this Cauchy problem, we can apply the result of Kajitani and Baba, and we know that a net of solution U epsilon exists. However, it is not only the point of the existence of this net of classical solutions. What we want now is to investigate the property in epsilon of the net U epsilon. And our aim, in order to say that a very weak solution exists, is to be able to estimate this U epsilon and to get estimate of this type, some negative power of epsilon. Okay, so how do we do this? This is the critical part. We need to go through the classical proof, right? So we need to go through the theory that has been developed before us, and we need to have a very precise knowledge of all the estimates. In the classical theory, so you can look at the paper by Cagitani and Baba, but also you can look at some of the previous papers by Alexander, Alessia, and Marco, you will see that in many estimates, because they were not dealing with the parameter epsilon, where they simply say, okay, there is a constant, and that's it. I mean, for us, this is not enough. We need to understand how that constant depends on all the ingredients of our problem, depends on the coefficients, on the regularization method, on the mollifier, and so on. All right, so before going through a sketch of the proof, let me give you the definition of very weak solution, because I've spoken a lot about very weak solution, but actually I didn't write down the precise definition. So a net in this space is an H infinity very weak solution of our Cauchy problem if there exists B infinity moderate regularization of the principal coefficient and the x part of the t part, of the coefficients in the lower order terms. If there exists B infinity moderate regularization of the lower order terms bj's, and also H infinity moderate regularization of the right-hand side and the initial data, such that for every fixed epsilon, U epsilon solves the regularized Cauchy problem, and it is also H infinity moderate. So what does it mean, H infinity moderate? Well, it means that when I take now the net U epsilon and I consider its Sobolev norm of any order m, I can always write an estimate of this type. So for every m, there exists n such that this is true. So this means to be H infinity moderate. In this kind of analysis, when I talk about regularizing method and when I talk about mollifier, to make my life easier, sometimes I usually work with epsilon, but to be honest, we will need to replace epsilon with a regularizing scale, which basically means to replace epsilon with some omega of epsilon, which is a positive scale converging to 0. But in general, we will work with this mollifier, and at the end of the proof, we will choose omega epsilon in such a way that we can get an H infinity moderate net U epsilon. Okay, so this is the theorem. Alexander, Alessia, Marco, and I have worked on this problem, let's say last year, and we've published 2 papers. So this is the first result that we proved, which is a theorem about existence of a very weak solution of H infinity type. So it is basically the summary of what I told you so far about the different coefficients, about how we regularize them. So it is an existent result. Later on, I will tell you a little bit about the uniqueness and how you need to frame uniqueness in this context, because it is slightly different from the idea that you might have in mind. Okay, so I would like to give you a sketch of the proof. Actually, I don't really want to go through the technical details, but I just want to give you a flavor so that you can understand what are the main points in this kind of mathematical analysis. Okay, so the main idea, which comes from the treatment of the Schrödinger operator in the classical theory, or if you want also the treatment of p-evolution operator, is to find an invertible operator that will allow us to write our problem in a simpler way. So this is the key. So the idea is, okay, my problem is too complicated. What I want is to find a way to transform it into another one, which is much simpler. And the operator that I'm using in this transformation, this E lambda, depends on the principal part of the operator S. Okay, so clearly, if I'm working in the classical context, I will not have any epsilon there. But because I'm working on a family of regularized operators as epsilon, then my invertible operator will also have the parameter epsilon in it. Okay, so I find this invertible operator, okay? I use it in transforming my problem. And because this invertible operator has simplified my problem quite a lot, I'm also able to write down a very precise estimate of the solution. If you look at the papers by Alexander, Marco, and Alessia, where they use this method, but in the case of regular coefficients, they proved this estimate, but here there was just a constant. That's it. So when we started to work together, we actually had to go through quite a lot of technical difficulties. So we had to go back to every step in the proof because we really needed to understand how this constant was depending on all the ingredients in the problem. And we ended up with this sort of a nasty object here, which is actually quite useful because it tells us precisely how the constant is depending on the Sobolev order, the dimension of the space. These numbers here, they come from the coefficients, so they are like the order of the distributions in the coefficients, so they depend on the structure of the distribution and so on. Okay, so we have transformed our problem, okay, so using this invertible operator, okay, we apply the estimates that we have obtained, and we end up for the solution U epsilon with an estimate of this type, where, if you see here, we clearly have a very precise way to say what these constants here are and from what they depend on. And this is really the main point of our argument. So to be able to have this very precise knowledge of the net U epsilon. So once we arrive at this point, then we are actually in a very good situation because now we are able to choose the kind of regularization, the kind of net that we need in our convolution to be able to obtain here for U epsilon an estimate of the type a certain negative power of the parameter epsilon. So I was simplifying my argument. So here I always wrote epsilon, but actually you will need to think here to replace epsilon with the scale over omega epsilon. So in conclusion, which omega epsilon shall we choose? Well, we will choose a scale of this type. And when I give this talk, I always like to remember the kind of label that Alexandra used in the tech file to label this formula. So I believe use something of the type the rise of the evil, right? Because clearly this omega epsilon looks very, very nasty, right? But if we go back to the previous page, it should not surprise you very much, because here you see there is an exponential, but then there is another exponential, and so on. And in particular, the point here was also to make sure to choose a scale which does not depend on the Sobolev order, so that we can prove we can use the same scale for all the Sobolev orders, and therefore we can prove the existence of an H infinity very weak solution. Oops, sorry. Okay. So we also want to stress the fact that in order to obtain our H infinity moderate net, and therefore our very weak solution, this kind of positive scale omega that we are using is necessary for the regularization of the coefficients of order 1 and order 0. While for the principal part, we can actually still use omega epsilon equal to epsilon. Okay. So we managed to prove existence of a very weak solution, because in other words, we managed to prove that a net of classical solution exists and it is H infinity moderate. But what about uniqueness? Well, uniqueness is intended in a different way with respect to the classical theory of PDEs and the Schrödinger operator. And this is due to the fact that we are using a regularizing method. So the first question is, what about uniqueness? And then the second question is, what happens when actually our coefficients are regular, and therefore we know that a solution exists? So if I'm using my method on a problem that is already regular, what do I get? So I get a very weak solution, but what is the relation between the very weak solution and the classical solution that I know to exist? So I will try to answer this question in the last few slides. Okay, so uniqueness is intended in terms of perturbations with the nets that are going to 0 when epsilon tends to 0. And these kind of nets are called negligible, so they are called H infinity negligible. And uniqueness is stated as in this proposition. So if I perturb my coefficients with some negligible nets, that what I'm gonna generate is another very weak solution, but it is not very much different from the one that I obtained earlier. So the difference between the two of them is also negligible, is H infinity negligible. And what does it mean to be H infinity negligible? Well, it means that the nets that I'm adding here, when I perturb the coefficients, they tend to 0, but faster than any positive power of epsilon. So this is how we mean uniqueness in this context, right? So we can say that a very weak solution is negligible, is a unique, modulo H infinity negligible nets. Now, if I am in the regular case, so if I consider this problem and I am under the assumptions of the classical theory, so under the assumption of the Kajitani and Baba result, so let's assume that I don't realize that and that I do the regularization anyways. This is not a problem because I do the regularization, I generate a very weak solution, but because my theory has been constructed in a good way, then any very weak solution will converge to the classical solution when epsilon tends to 0, which means that we have developed a theory which is consistent with the classical one, which is clearly something that we wanted right from the beginning. I don't know how much time I have left. Do I still have like Few minutes?
Yes, Professor,
Manuel?
between
Okay, good.
15 or 20, yes.
Oh, okay, so fantastic. All right, so in the few minutes that I have left, I would like to tell you a little bit about a second paper that we wrote, always with Alexander, Marco, and Alessia, which is the temper distributional case. So in the problem that we have addressed so far, we were always using like coefficients that are distribution with compact supporting T. We would like to be a little bit more general, okay, in particular concerning the assumption that we have in time, but somehow we choose a simpler problem because we decide to take a of t equal to 1, but here we have lower the terms that are not a function in t times a function in x, they are just a function in two variables t and x. Okay, so we assume that Cj and C0 are continuous in time and temper distribution with respect to x, and then we have a similar hypothesis for the right-hand side and the initial data. Okay, so now, when I regularize this problem, I'm gonna do it in a slightly different way with respect to before. Because what I want is that when I regularize all the coefficients, I end up with nets of rapidly decreasing functions. This is in general not true if I just do this regularization, because I will end up with some polynomial behavior. So I need to introduce here another net of functions defined in this way, okay, where this phi is a function equal to 1 at 0. So you see, there isn't just one way to regularize the coefficients. Your regularization method really needs to be adapted to the kind of problem that you want to study, okay? And you might need to do some small changes, or maybe to use two different kinds of modifiers and so on. And this is a typical example. Okay, so now again, with my same group of collaborators, we have proven that under this hypothesis, this Cauchy problem is very weakly well posed in the sense of the Schwarz space. So what does that mean? It means that one can prove that a very weak solution of Schwarz type exists. So you have to think that all the estimates will be done according to the semi-norms of the space S. Okay, so a very weak solution exists, and it is unique modulo negligible changes that are also of rapidly decreasing type. This kind of result can look in line with what we have done before, but actually, in order to prove it, we needed to prove that when the coefficients are regular, so when they are rapidly decreasing, actually the classical Cauchy problem without regularization is well posed in the Schwarz space. So we proved that result, which was like something new in the classical context, and then we proved the very weak version. So concluding, what I find very interesting in this kind of mathematical analysis is actually the possibility of studying a problem at different levels. We always think about singular coefficients, but sometimes in order to prove the result for singular coefficients, we need to prove first some improvement of the classical theory. So somehow you are proving two things, right? So you are learning more in the classical theory, and then you are expanding the theory of very weak solution. And the other point that, again, for me personally is very interesting in this theory is that you need to reach a very high level of precision when you do your estimates, which means that you really you really need to track the dependence of the constants that you are using in your estimates at every level of the proof. And this level somehow of precision is a quality that becomes very useful not only in this kind of analysis, but also in other areas of mathematics. So I have actually finished everything I wanted to say, so I will stop here and I'm very happy to answer any questions you might have. Thank you.
Thank you, Professor Claudia, again for joining us today with your presentation. Very interesting. We
My
had
pleasure.
a lot of people connect, almost 60 attendees here and more on the. We'll see the YouTube recording. Do anyone here in the presentation have any questions?
And thank you also for joining so early. What time is it there?
Here in Guatemala, it is
It's
9:40.
9. Okay.
Yeah. Okay, let me check the chat. You can ask by the chat. Oh yes, Luis Yapu, please feel free to ask. Yes, Luis Yapu. Luis Yapu, do you have a question?
I believe I saw 2 hands up. Luis and Juan.
Juan Pablo? Do you have a question, Juan Pablo?
Yes.
Please.
Just a curiosity. In a paper of Carlos Muñoz, Rusansky, and Dr.
Yes.
Magabekov, they discovered that the discontinuities on the coefficients produces certain echo.
Yes. Yeah. I remember that paper. Yes.
In this case, and in the case of the Schrödinger equation, what is the implication of singular coefficients?
Yeah, no, it's a very good question. So we haven't done that numerical analysis yet, but I believe it's definitely something that one could try to understand. I believe probably one will need to simplify a little bit the model, right? To be able to run some experiments and to see if one can get the same kind of eco effect. Because if I'm not mistaken, in the paper by Michael, Munoz, and so on, they were probably working with like the classical Schrödinger operator. Maybe they had like, maybe they just had like one lower the term or the potential. So I guess one will probably need to simplify the model a little bit, right? Because in the kind of treatment that I have given now, I've been really, really general, right? But it's definitely a good direction, right? So if anyone wants to work, if you have ideas, then you can also contact me. We can try to look at it together. So I believe there are possibility of expansion. In the past, I had a PhD student that was running some numerical experiment, but they were more on the wave equation with a singular coefficient.
Thank you.
You're welcome.
Luis Yapu, do you have a question?
Yes,
Please.
yes, thank you. I have a question. It's related to the transformation you use.
Yes.
Do you use a gauge transform using the frequencies also, or only using the space? Which is because sometimes you do.
Okay, let me try to find it. This lambda here, right?
Yes.
Yeah, so this lambda here really depends on the operator, right? So it depends on I believe it depends on A of t and also on the coefficient of the first order. So it will depend on epsilon as well. Let me see. Yeah, so here on the slides, I don't have the precise formula, but in the paper, you can see how lambda is constructed. And actually, in the paper, now that I think well, there are two proofs. So there is the proof in space dimension 1, which is actually easier when you can really see explicitly how lambda is constructing, and you can go through like all the steps. And then there is like the more general proof in Rn, which is a little bit more complicated. So I would suggest probably to have a look at the one in space dimension 1 first. Does that answer your question?
Okay. Thank you.
Yeah.
He says it answered the question. Thank you,
Okay,
Professor.
good. Let me see. Yeah. Okay, you were writing in the chat. Thank you. Thank you very much. Yeah, no, Martial, I also believe that the numerical aspect will be interesting to be explored. I'm not a numerical analyst, unfortunately, so I always need like the support of some numerical analyst. But in the past, I have done something for the wave equation in collaboration with a former colleague who is a numerical analyst. So for instance, the numerical analysis could be also interesting to understand what happens when we change the modifier. How are the two very weak solutions related? Okay, so there are things that probably in an analytical way we cannot really do. Maybe we don't really have a precise analytical proof, but we could get some insight from a numerical point of view. Any other questions? Let me see, there is something in the chat.
I have a question, Professor Claudia Gareto.
Yes, please. Please
I
do
think
on.
it was slide 19. Slide 19, right?
19. Okay, so let me, before, I believe there was a question online in the chat, Duan, sorry.
Manuel?
Okay, which method is the best to use the coefficient? I don't believe that that there is the best method in absolute, right? So it really depends on the problem. Okay, it really depends on the problem that you have to deal with. Okay, slide 19. Sorry, I'm going here down 16, 17. Here. Okay.
Oh,
Are we
I
here?
see. Okay. Okay.
Here? Okay, this one. Yes. Here we
Yes.
are.
Okay. My question is related to the order of the derivative in time, right? Is one. My question is if you have considered the case of more close to wave equation, right? When you have second order in derivative in time. More close to wave equation.
Yeah. No, we haven't done that because I believe this is somehow this is the format of the P evolution operator, right? With P equal to 2. Okay. But possibly there is the possibility, right, not to do something different. I mean, for the wave equation, I have those papers on hyperbolic problems, hyperbolic equations and systems, right? And there is a paper, there is this paper in ARMA with Michael, where we, for the wave equation, right, where we have considered singular coefficients, but what we got was a very weak solution of Gevrey type. Yeah,
Okay.
and there was also some recent work in collaboration with Bolis, Sabiptek, and that was more on hyperbolic systems obtained as reduction of M-order hyperbolic equation into a system. But I believe the focus there was more on the fact that you might have multiplicities. And having multiplicity, then you usually, it's become difficult to prove infinity well posedness or Sobolev well posedness, and you have to work with Gevrey classes. Yeah.
Thank you very much.
Thank you. Thank you all for attending and for the many questions.
Thank you, Professor Claudia. Thank you again for accepting our
My pleasure.
invitation. We hope to have you here in the future soon.
Of course,
It
of
was
course.
a really,
Thank you.
really interesting presentation, and I think every and each one of us learned a lot from you today. Thank you very much.
Yeah, indeed, and feel free to contact me if there are some problems that you want to discuss. The beauty of mathematics that is that there are no borders, right? So we can always work together, even if we are into different parts of the world. And I speak Spanish as well. So, muchas gracias y hasta luego.
Gracias. Thank you.
Thank you. Thank you, everyone.
Thank
Bye
you.
bye. Bye.
And to everyone, we will have a break until 18 Central European Time, where we will have the presentation from Professor Diego Esteban Gutierrez Valencia. And we will see you until then. Thank you very much.
Thank you very much. Muchas gracias, Claudia. Thank you very much, Manuel.
Good morning, good afternoon to everyone. Dear Professor Diego Gutierrez, I see you have already joined the meeting. Thank you very much for joining us today. We will be beginning in a couple more minutes. I would like to remind you that you have 45 minutes for your presentation, and we will have 10 to 15 minutes for questions, okay? Could you try to share your screen, please, to check everything is working?
Can you see the presentation?
Yes, we can see the presentation. Thank you.
Excuse me, can I get question? Mm, the presentation is contribution may I use Spanish language or is fundamental use of English?
The presentations are in English. Do you feel comfortable speaking in English? Or
I'm not very sure of my language. I would prefer making it in Spanish. However, all the writing is made in English.
okay. Feel free to do it in Spanish then, no problem. Thank you very much.
Thank you. Esperaré indicaciones al respecto.
Okay. Okay, so I think it is a good time to begin. Thank you very much, Diego, for joining us today. Diego is from Instituto Tecnológico de Chilpancingo in Mexico. His presentation is about a singular integral operator for the Lamena-Fier system in the unique disk. Muchas gracias, Diego, por acompañarnos hoy desde el Instituto Tecnológico de Chilpancingo en México con su presentación titulada de un operador singular para el sistema Lamena-Fier en el disco unitario. Muchas gracias, Diego. Siéntete en libertad de usar el tiempo como gustes.
Muchas gracias, profesor Manuel, por cederme la palabra. Y antes de iniciar, quiero agradecer a todos por estar presentes y por haber aceptado pues, esta contribución de un grupo de trabajo acá en México. Pues, bueno, estará orientada la presentación en este orden. Y pues quisiera darles un pequeño contexto de dónde surge este problema. Surge a partir de la teoría de elasticidad lineal, a partir del estudio de las deformaciones de un cuerpo, es lo que se conoce como el sistema de Moebius. En un principio fue descrito por Gabriel Lamé en los años 1800, pero posteriormente fue Navier quien, ante la Academia de Ciencias de París, propuso un sistema de ecuaciones en derivadas parciales para objetos sólidos. Sin embargo, con trabajos previos, hemos tratado de estudiar este sistema en el caso bidimensional o en el caso plano. Si se quisiera hacer un análogo, sería como una lámina de material que se somete a deformaciones de tracción. En un principio, este sistema de ecuaciones en derivadas parciales estaba planteado para algo que se llaman los vectores de tracción. Sin embargo, se puede reformular para lo que sería un vector de desplazamientos que es más útil al estudiar las deformaciones en la frontera. Estos coeficientes lambda y mu, bajo este contexto, son propiedades físicas de los materiales, se les llaman parámetros de Lamé, y delta va a denotar el operador de Laplace en R2. Si no tenemos fuerzas que actúen sobre el cuerpo, pues ese sistema se va a reducir, sistema número 2. Y como lo había mencionado, los parámetros lambda y mu deben cumplir ciertas restricciones de índole física que están planteadas en la parte inferior derecha. Con el uso del análisis complejo, este sistema se puede transformar en una única ecuación a través de estas cuatro identidades que se muestran en estas dos líneas. Y pues resulta entonces esta ecuación número en derivadas parciales de segundo orden, la ecuación número 3. En lo sucesivo voy a mostrar algunos resultados en donde aparecen estas letras alfa, beta, alfa asterisco y beta asterisco, que son unas transformaciones muy sencillas que se hacen para que no pierda simetría la ecuación. Vamos a hablar ahora de unos preliminares al respecto para posteriormente tenerlos en cuenta, y son las clases de funciones de Lipschitz de orden superior, que son un poco las generalizaciones que vamos a tratar al respecto. Básicamente, las clases de funciones de Lipschitz son el análogo a las clases de funciones de Holder, que es el análisis complejo. Y esta definición me gustaría centrarla un poco más en esta última línea, o en estas tres condiciones de acá. Son tres condiciones que deben estar acotadas para establecer si esta colección de funciones está dentro de Lipschitz o no. También hacemos uso del teorema de extensión de Whitney en su versión compleja. Aquí no tratamos un poco la demostración, pero va a ser de utilidad. También, pues vamos a definir, o se va a entender lo que es el operador integral singular con un núcleo de Cauchy a través de lo que es la ecuación número 4, y se calcula de esta manera. Resulta que antes de poder hablar de la invariancia del operador integral singular asociado a la ecuación compleja de la mena abierta, es importante hablar de algo llamado el problema del salto. Este problema de salto es un tipo de problema de contorno de Riemann, es un caso particular, y esto se trabajó anteriormente. Y a través de este problema de salto se obtuvo un resultado que es el que analizaremos, o que es el foco de atención. Una vez solucionado el problema de salto, se define lo que el grupo de investigación llama transformada de la Cauchy. ¿Por qué? Porque esta ecuación número 6 está dada en términos de integrales de tipo Cauchy, y pues bueno, tiene su origen en el sistema abierto. si podemos notar, esta transformada está dada en términos que pertenece a lo que son las clases de funciones de Lipschitz y tiene su origen en el problema del salto. Entonces, aquí surge naturalmente eh, preguntarse si el operador integral singular asociado a esa transformada eh, cumple la propiedad de invariancia para las clases de funciones de Lipschitz de orden 1 más no, donde no es un número que está entre 0 y 1 estrictamente, y la frontera en este caso es el círculo unitario. De esta forma, pues es interesante preguntar si los valores de la frontera, cuando me aproximo por el interior o por el exterior, ¿sí? Satisfacen que esta colección esté igualmente cayendo sobre las clases de Lipschitz. Ahora bien, vamos a utilizar un poco, ¿sí? Lo que es la definición de las clases de Lipschitz de orden superior, y a utilizar una transformación de esta función original en la suma de un polinomio más un resto. ¿Esto por qué? Porque nos ayuda a simplificar un poco los cálculos que son posteriores. Cuando hacemos esta transformación, las posteriores integrales que se usan al respecto se reducen mucho para poder establecer lo que son los operadores. Entonces, a través de la definición de lo que es el operador integral singular clásico, se han calculado o se han obtenido lo que son los operadores integrales singulares, que sería esa colección de superíndice S00, S01 y S10. Entonces están dadas por las integrales 1 y 7, la integral número 8 y esta sucesión de integrales número 9. Ahora, ahora sí el problema central, un poco más planteado, que quisiera compartirles. Para probar que este operador, verificar si vuelve a caer dentro de esta clase de funciones, se tiene que demostrar que estas tres condiciones estén acotadas por este factor que está en el lado derecho. Aquí J es un multiíndice, en este caso sería el multiíndice 00, el multiíndice 10, el multiíndice 01, para poder hacer esta conversión de aquí. En pocas palabras, habría que verificar que esta expresión, este primer línea hasta el cursor, esté acotada por una constante positiva, multiplicada por el valor absoluto de t menos tau a la 1 menos 1. Esta segunda línea, que esté acotada por exactamente una constante positiva, valor absoluto de t menos tau a la nu, y esta de acá abajo también, esté acotada exactamente por antes de proseguir con lo que es la técnica que se utilizó, mm, se hicieron uso de algunos resultados auxiliares. El primer resultado auxiliar es el lema número 5. El segundo lema auxiliar es este de aquí, que trata de que si una función continuamente diferenciable es de tal forma que sus derivadas parciales son continuas con exponente nu, entonces la función y sus derivadas parciales están en clase de Lipschitz de orden 1 más 1. Y finalmente se hace el uso de estos lemas, ecuaciones auxiliares que están aquí, que son una especie de acotaciones para este tipo de integrales. Entonces, mm, parte de la técnica que se tiene que usar para demostrar esta invariancia es tratar de llevar todas las acotaciones a algo de este estilo o bien a algo del estilo del lema número 5. De esta forma, al calcular explícitamente lo que llamamos, lo que llamo yo resto, un resto 0,0 del operador integral singular, se obtiene lo que es la expresión i, que está dada por toda esta ecuación de aquí, y aquí hay una particularidad. Si observamos los diferenciales y los núcleos están iguales, es decir, no están conjugados uno respecto al otro, y esto es de suma importancia. En cambio, cuando cuando presento J, si observamos, aquí tenemos los diferenciales que están totalmente conjugados. Entonces, para demostrar un poco cómo funciona la técnica en este sentido, es importante separarlas un poco. La primera integral y sub 1 son funciones que originalmente viven en el espacio de Lipschitz de orden 1 más 1. Entonces, si tratara yo de acotar esta integral, pues la misma contenencia de estas funciones en las clases de orden de Lipschitz me permite acotarlo. Esta integral I sub 2 es un poco más delicada para tratar, y nos vamos a hacer uso de los lemas vistos anteriormente. Y la integral I sub 3 va a hacer uso de lo que es el lema de las derivadas parciales. Entonces, como lo mencioné, el primer término integral llamado I sub 1 está acotado, pero el I sub 2 hay que utilizar un tipo de reescritura para poder acotarlo. Entonces, esta integral dada por I sub 2 se reescribe en términos de ciertas identidades para posteriormente usar lo que es el lema número 7. ¿Sí? Entonces, en este punto, lo que se hace es una reescritura de los denominadores para llevarlo a la forma del lema número 7 y poder votarlo. Como dentro de los lemas que permiten acotar las integrales no están incluidos estos términos logarítmicos, aquí es cuando se usa un poco el lema definido anteriormente respecto a las derivadas parciales. ¿Y esto en qué sentido? Bueno, lo que, lo que hacemos al respecto es definir esta función f de z y estimar sus derivadas parciales y su derivada parcial conjugada. Aquí, efectivamente, podemos hacer uso de un teorema de Plemel-Privalo acerca de la invariancia del operador integral singular clásico, ¿sí? Porque esta función que está dentro del término integral y esta función de aquí que está dentro del término integral, pues son funciones que están dentro de la clase de Lipschitz de orden 1. como quien dice, son Lipschitz continuos con exponente nu. Entonces, al ser Lipschitz continuos con exponente nu, hacemos uso del problema presentado anteriormente y toda la función en sí misma, pues, está dentro de la clase de Lipschitz, pero de orden superior, en este caso, 1 más 1. Y bueno, al producirse esta contenencia para este cúmulo de funciones, podemos establecer, ¿sí?, que toda esta integral I sub 3 está acotada por este término de orden 1, 1 más 1. Entonces, la estrategia con el resto de integrales es básicamente la misma. Cuando haya términos logarítmicos, lo que se hace es tratar de llevar todo al uso de este lema. Y cuando hayan términos que hagan uso de estos factores en el denominador, lo que se hace es convertirlos aritméticamente a situaciones que se parezcan a los lemas 5 y 7. Esa es la estrategia que básicamente se usa. Entonces, los restos 1, 0 y el resto 0, 1 son un poco más sencillos, entre comillas, porque no gozan de términos logarítmicos. Pero si surge, si surge una cuestión, mm, me voy a permitir regresarme un poco. Mm, Aquí, sí. Si observamos nosotros esta integral j, aparecen unos términos, ¿sí? Que aquí en el resto 0, 0, pues los podemos acotar a través del lema de las derivadas parciales, pero cuando se trata del resto 1, 0, 0, 1, este núcleo de aquí, ¿sí?, si observamos en el denominador, no está conjugado, pero el diferencial respecto de las variables sí está conjugado. Tratar de aplicar el teorema de Plemel-Privalov para este tipo de términos no es tan evidente. Más allá no se puede aplicar, entonces la invariancia en ese sentido no, no está garantizada. ¿Cómo se resolvió ese problema? Pues bueno, estamos en el círculo unitario, entonces lo que podemos hacer es que estos denominadores se pueden transformar a través de la propiedad de que en el círculo unitario, 1 sobre chi por chi conjugado es igual a su norma. Entonces, haciendo uso de esa pequeña identidad, pero que en este contexto posee mucha fuerza, lo que hace es transformar estos denominadores en su versión conjugada a través del círculo unitario. Entonces, lo que me haría es mezclarme esta parte con el conjugado del diferencial y me permite a mí reorganizar y arreglar un poco este problema. Entonces, de esa forma, la herramienta o estar en este caso en el círculo unitario es bastante fuerte y de esa forma es que podemos solucionar ese problema para estas dos expresiones de aquí. Y pues bueno, finalmente de esa forma garantizar lo que es la invariancia de el operador integral singular de toda su clase. Este, eh, yo creo que de mi parte es todo y pues agradezco a ustedes por escucharme y por la invitación.
Ok, profesor Diego, muchas gracias por su contribución. Muy interesante la presentación. Thank you very much, Professor Diego, for your presentation. Very interesting. Feel free to ask any questions you have. They may be in either English or Spanish, and we will do our best to translate them as
Thank you.
as faithfully as we can. Okay? You can write on the chat. Pueden escribir en el chat. Or raise your hand, pueden levantar su mano. Mientras tanto, yo quisiera saber si qué tan importante es el, el parámetro nu entiendo que es de regularidad extra que le piden a las funciones. No sé si nos puedes compartir algún dato sobre ello, ¿no? No sé.
Cuando recién inicié a trabajar con, ese, con esta cuestión, mm, pues hay varias cosas. La primera es que cuando hacemos la transformación de aquí al utilizar esto, nos dimos cuenta que hay una relación aquí de simetría entre este alfa y este beta que me permite más adelante, realizar ciertas operaciones y estos términos que contengan alguna combinación de alfa y de beta, que pues al mismo tiempo tienen combinaciones de lambda y b, um, ellos se anulan y me permite seguir adelante a mí con las pruebas que necesito. Esa es una propiedad interesante de ellos. Y ya desde el punto de vista físico, no ahondé mucho cuando recién inicié, pero cuando estas condiciones no se cumplen, eh, resulta que se trabajan con materiales. Por ejemplo, cuando el MO es negativo, llegué a leer alguna vez que se trabajan con materiales que se les llaman metamateriales. Y entendí que son materiales que cuando, eh, cuando uno los comprime, en vez de comprimirse, ellos tienden a expandirse. Este se le conoce como el módulo de tracción. Esa fue una de las propiedades interesantes que encontré cuando estaba trabajando inicialmente con estos sistemas de ecuaciones.
Ok, muchas gracias, profesor Diego. ¿Alguna otra pregunta? Any more questions? Uh, I think that is all the questions we have. Creo que son todas las preguntas que tenemos en este momento. Muchas gracias, profesor Diego, por su interesante presentación. Se lo agradecemos mucho por haber formado parte de esta conferencia y esperemos que pueda participar en más actividades de ICMAM en el futuro. Muchas gracias.
Les agradezco a todos ustedes por haber aceptado esta pequeña contribución, por la invitación. Y claro, sería magnífico seguir contribuyendo un poco más y para la próxima creo que voy a aprender más inglés, que sí lo leo, pero
Ok,
un
no
poco
hay problema.
raro al
Muchas
hablar.
gracias.
Gracias a ustedes por la invitación, muy amable. Que tengan un buen día.
Igualmente,
Hasta
thank
luego.
you. Gracias. Hasta luego. Thank you to everyone in the meeting. We'll have a little break until 19 Central European Time with the presentation from Marcos Antonio Herrera Peláez, which is related to the Lamena Fear system, in this case in RN. Uh, until then, thank you very much. Okay. Professor Marcos Antonio Herrera Peláez, are you here in the meeting with us right now?
Hola, ¿qué tal? Sí, sí, estoy aquí.
Hola.
Hola, hola.
¿Desean su presentación en inglés o en español?
Preferiría en español, por favor.
Ok. Intente compartir pantalla, por favor, para ver que todo esté funcionando correctamente.
Ok, sí.
Ok. Excelente, gracias. Okay, good morning, good afternoon to everyone of the attendees. Thank you very much for joining us again. Right now we have Professor Marcos Herrera Peláez from Universidad Autónoma de Guerrero, Mexico, with his presentation, A Young Problem for an Iterated Lamina Fear System in RM. Muy buenas tardes a todos. Gracias por acompañarnos el día de hoy. Ahora presento al profesor Marcos Herrera Peláez de la Universidad Autónoma de Guerrero en México con su presentación titulada Un problema de salto para un sistema iterado de la MENAFIR en RM. Así que, profesor, muchas gracias por acompañarnos y por su presentación. Le cedo la palabra y le recuerdo que dispone de 45 minutos para su presentación. Muchas gracias.
Muchas gracias por aceptar mi plática, por darme este espacio. Muchas gracias a todos por estar aquí. Bueno, voy a empezar con esta charla. La presentación la tengo en inglés para que las personas que no dominen el español puedan ir sellando un poco. Igual al final, si hace falta alguna pregunta, pues estoy en la mejor disposición de responderla. Cualquier duda o aclaración, no duden en levantar la mano, participar, con el fin de que pues esta charla sea lo más nutrida posible, ¿no? Así que bueno, voy a empezar. Eh, Bueno, de manera general, vamos a empezar hablando un poco sobre las representaciones integrales. Mm, como sabrán, en ecuaciones diferenciales parciales, una de las herramientas, digamos, importantes a la hora de estudiar pues, ese tipo de problemas son las representaciones integrales. En ese trabajo vamos a considerar ecuaciones diferenciales parciales de iteraciones del operador de Dirac definido en RM, definido como se muestra en la pantalla, donde aquí pues este parcial x sub i denota la parcial con respecto de la variable x sub i. Específicamente vamos a estudiar una ecuación iterada, que es esta que presentamos aquí con el número 1, donde alfa j y beta j son números reales. Esta surge del sistema de la Menavier, ¿sí? Entonces, ese sistema de la Menavier lo voy a presentar más adelante, de dónde surge y cuál es su, digamos, su relevancia en la física, pero de momento nos quedamos con que pues, lo que queremos obtener es, en principio, representaciones integrales asociadas a este sistema iterado, lo cual nos va a permitir después resolver un problema de salto. El problema de salto no es más que un problema de tipo Riemann-Hilbert, eh, asociado con esta ecuación. Como preliminares vamos a empezar definiendo lo que son las álgebras de Clifford, que son el marco en el que nosotros trabajamos ¿sí? Eh, no sé si algunos de ustedes estén familiarizados con esta definición, pero de manera general podemos decir que las álgebras de Clifford son una generalización de los complejos y los cuaternios, ¿no? Con esa definición que tenemos aquí, definimos reglas de operación que nos permiten, por ejemplo, tomar de manera general un RPQ, una álgebra de Clifford definida con, perdón, una álgebra de Clifford que toma elementos de los números reales. Y para casos particulares de estos PQs, obtenemos, por ejemplo, que los números reales coinciden con el álgebra de Clifford R00, los números complejos coinciden con R01 y los cuaternios coinciden con R02. Nosotros de manera general vamos a trabajar con funciones en R0M y en adelante pues vamos a, como les comentaba, trabajar sobre subconjuntos de RM que toman valores en R0M. Las nociones que tenemos en, digamos, en los complejos o en álgebra clásica de continuidad, diferenciabilidad e integrabilidad de funciones R0M evaluadas, pues se entienden en este caso componente a componente, ¿no? En particular, los espacios de funciones continuamente diferenciables o k veces continuamente diferenciables se denotan con estas letras, ¿no? C a la k, C sub k y L a la p, donde el conjunto E siempre va a ser un subconjunto de Rm. Así, usando los vectores de esta base de R0M, del álgebra que definimos, el operador de Dirac, que es un operador de primer orden, operador diferencial de primer orden, denotado como ya vimos como delta o parcial X, para funciones de clase C1 en Rm, se define de la siguiente manera, ¿no? Como ya lo habíamos visto anteriormente. Algo importante de este operador y que lo vamos a usar en adelante y que se usa mucho, y de hecho es la razón principal por la que trabajamos bajo este contexto de las álgebras de Clifford, y es porque este operador de Dirac factoriza el operador laplaciano en Rm, en el sentido de que al iterar dos veces este operador, obtenemos menos el laplaciano. Entonces, renombramos a las funciones monogénicas, que sería el análogo como a las holomorfas en variable compleja, a las funciones que anulan este operador de Dirac por la izquierda, y monogénicas a la derecha, pues a las funciones que anulan este operador por la derecha. Bueno, creo que se me olvidó mencionar que aquí, que este operador de Dirac, en general, hay que distinguir entre aplicarlo por la izquierda y por la derecha, porque en general las álgebras de Clifford son unas álgebras que no son conmutativas. Entonces hay que distinguir entre aplicar el operador por la izquierda y por la derecha. Y de manera general, podemos iterar este operador pues, no solamente dos veces, ¿no? Sino las veces que queramos. Entonces, las funciones monogénicas o k-monogénicas van a ser aquellas que anulen este operador iterado k veces. Igual se distingue entre k-monogénicas a la izquierda y k-monogénicas a la derecha. En particular, las funciones bimonogénicas corresponden a las funciones armónicas evaluadas en este R0M. Y surgen también otro tipo de funciones interesantes, que es cuando el operador de Dirac actúa, pues digamos, en ambos lados, ¿no? Por la izquierda y por la derecha. Entonces ahí surgen las llamadas funciones infrapolimonogénicas. Para k igual a 2, estas funciones son simplemente llamadas inframonogénicas. Entonces, en adelante también vamos a asumir por simplicidad que omega tiene una frontera suficientemente suave, gamma. Entonces el teorema de Stokes, análisis de Clifford nos conduce a la fórmula de Borel-Pompeyo, que es esta, que me relaciona aquí un operador de frontera, un operador de Cauchy, y un operador de Teodorescu, ¿no? Que es este. En particular, esta fórmula de Borel-Pompeyo lo que nos permite es, recordemos que si la función es monogénica, el operador actuando por la izquierda de la función, pues cero, ¿no? Entonces, no se anula. Y esta fórmula de Borel-Pompeyo lo que nos da es una fórmula integral de Cauchy, digamos, ¿no? Esta fórmula de Borel-Pompeyo obtenemos la fórmula integral de Cauchy para instancias químicas. Estas fórmulas de representación integral nos permite también ahora obtenerlas de manera general, no solamente para el operador de Dirac iterado, digamos, perdón, el operador de Dirac aplicado una sola vez, sino ya iterarlo varias veces, cada vez, y así obtenemos también una fórmula de Borel-Pompeyo, digamos, de manera general para cualquier K. Evidentemente, también se puede obtener una fórmula integral de Cauchy de orden superior, digamos, para este operador. Y de esta misma manera podemos obtener fórmulas de representación integral para las infrapolimonogénicas, que recordemos que eran las funciones que anulan el operador, digamos, actuando por ambos lados, por la izquierda y por la derecha. Aquí tenemos un ejemplo de fórmula para las funciones infrapolimonogénicas. Evidentemente, por ahora solamente las vamos a mencionar así, ¿no? Para ir entendiendo que cada uno de estos operadores tiene su fórmula de representación para cada uno de estos operadores. Y bueno, ahora formulamos el problema que vamos a tratar el día de hoy. En teoría de elasticidad lineal, uno obtiene que el sistema de la Menavier en notación vectorial se escribe de esta manera. Entonces, aquí mu y lambda satisfacen esas desigualdades. De hecho, creo que este sistema ya lo presentó eh, nuestro colega en la plática anterior, la plática pasada, ¿no? Esta ecuación tiene que ver con nos sirve, mejor dicho, para describir sólidos elásticos, ¿no? En teoría de elasticidad lineal, tú tienes un material elástico y esta ecuación te permite describir cómo se comporta bajo ciertas condiciones ese material, ¿no? Entonces, este sistema de manera general no tiene una solución así general. Estos mu y estos lambda son valores que dependen del material elástico con el que estamos trabajando y se imponen esas condiciones para que, digamos, el modelo del material tenga sentido, ¿no? Y sobre todo también porque esto permite que ese sistema sea fuertemente elíptico. Si quitamos estas condiciones, el sistema puede ya no ser no solamente fuerte elíptico, sino que incluso puede ser elíptico. Entonces, mediante el uso del análisis de Clifford, podemos entonces reformular este sistema de la Menavier que teníamos anteriormente, que surge de elasticidad lineal, lo podemos factorizar en esta ecuación 3. Ahora, fíjense que ahora ya no aparece el laplaciano, el divergencia, el gradiente, ¿no? Como tenemos esos operadores, digamos, vectoriales, los convertimos ahora simplemente a esta ecuación 3. Es decir, las álgebras de Clifford nos permiten reescribir ese sistema en términos ahora solamente del operador de Dirac, en donde definimos ahora nuestros alfa y nuestros beta, van a ser estas constantes, ¿no? Que son reales y que dependen nuevamente de los parámetros mu y lambda. Y mediante esta reescritura, digamos, del sistema de la Menavier, pretendemos ahora pues simplificar nuestro problema y encontrar, o sea, conociendo la teoría que vimos antes sobre las fórmulas de representación, pues también nosotros ahora una fórmula de representación, pero para este sistema iterado que es más general. Entonces, digamos, el sistema de la Menavier es el, el que está arriba, este operador, ¿no? Y lo que nosotros pretendemos hacer, bueno, y si solamente nos quedamos con esto, que seguimos iterando este operador, ¿no? Lo seguimos iterando. ¿Qué pasa entonces con este sistema iterado? En este caso, entonces, el operador de la Menavier sería un caso particular de este operador iterado. Ahora, bueno, si desarrollamos este operador, si lo vamos iterando para j igual a 1, para j igual a 2, etcétera, vamos a darnos cuenta de que va a haber dos casos. Digamos, se van a juntar en dos casos, dependiendo de la iteración de este operador. Si cae sin par, obtenemos que la general esa iteración nos va a dar esta ecuación que tenemos acá. Y si cae par, nos va a dar esta operación. Fíjense que si K es impar, aparece el operador de Dirac actuando por la derecha, el operador de Dirac de orden K, evidentemente, y también actuando por la izquierda, ¿no? Sin embargo, cuando K es par, actualmente el operador de Dirac actuando por la izquierda, pero ahora nos aparece también actuando sobre la función en ambos lados. De manera general, tratar problemas con K impar, en donde solamente aparece el operador de Dirac, digamos, en ambos lados, es relativamente sencillo. Sin embargo, las cosas se complican cuando aparece este operador de Dirac actuando por ambos lados. Entonces, el estudiar esta ecuación integrada se reduce ahora a estudiar estas ecuaciones 4 y 5, ¿no? Recordemos la ecuación 4, la que surge cuando K es impar, y la ecuación 5 es cuando K, surge cuando K es par. Y bueno, de esto se puede deducir el siguiente problema, el siguiente teorema, perdón, que si K es impar, para una función f de clase C sub K en omega unido con gamma, y si además esa función satisface esta ecuación, entonces podemos obtener una fórmula de representación. Esa función f admite esta fórmula de representación integral que tenemos aquí. Es decir, ya tenemos de alguna manera una solución para este sistema iterado, ¿correcto? Y como teorema 2, ahora si es par, existe también una fórmula de representación para estas funciones. Es decir, si la función satisface esta ecuación, bueno, aquí me faltó un espacio, si satisface esta ecuación, en donde vemos que aparecen las funciones infrapolimonogénicas, también admite una fórmula de representación que sería esta, ¿no? En donde aparece, como podemos observar, la transformada de Cauchy de orden K, la transformada infrapolimonogénica de orden K que vimos en un principio, ¿no? Y en términos de estos términos, podemos expresar esta función o la solución a esta ecuación. Y bueno, en base a estas dos fórmulas de representación, esto nos conduce, nos incita a resolver un problema de frontera. Como ya tenemos una fórmula de representación, entonces nos invita a resolver este problema de frontera, que es el siguiente, ¿no? Si yo tengo esta ecuación iterada, ¿sí? Y las condiciones de frontera que yo impongo, pues yo quiero encontrar esa función u que me satisfaga este sistema, ¿no? Básicamente este problema de frontera, o problema del salto, es un tipo de problema de la clase Riemann-Hilbert, en donde yo tengo un dominio, ¿no? Que está partido de alguna manera. Yo lo que busco es encontrar una función u, ¿no? Que se satisfaga dentro del dominio y que fuera de ese dominio, bajo ciertas condiciones en la frontera, yo quiero como que juntar, vaya, esa función, ¿no? Como que juntar una sola función que me resuelva este sistema iterado, pero también que satisfaga estas condiciones de frontera, ¿no? Entonces, aquí, pues, estas parciales, sea la u más y menos de nota, por la función, si los límites correctos, y es lo que presenta este problema. Como está, tenemos el problema así como el anterior, en donde tuvimos fórmulas de representación, ya está entre un K y un K impar, debido a que tenemos dos fórmulas de representación, requerimos de distinguir eso, ¿no? Entonces, para K impar, tenemos que esta función no satisface el iterado, y las condiciones de frontera eh, que imponemos aquí, ¿no? Ahora, como había comentado antes, para el caso par suele ser más complicado en general encontrar una fórmula de representación y resolver problemas de frontera. Para el caso en que aparezcan funciones infraprimánicas, es decir, funciones en el operador de por izquierda,
Mamá,
al
¿y
mismo
usted sí entiende este álgebra?
Perdón, continúe, por favor.
decía que en general para, para el caso de cáncer tenemos por relación un poco más compleja que vamos a ver ahorita. Sin par, como que la solución U no es del todo pues tediosa, digamos. Sin embargo, para el caso par requerimos de algunos resultados auxiliares. En este caso vamos a necesitar del lema número uno, que es el que tenemos a continuación, que me dice que si u de x es igual a esta sumatoria, ¿no? Esa integral de frontera. Recordemos, este es el núcleo de mi integral. Pues yo tengo que el salto de esa función va a cumplir esta propiedad, ¿no? En donde es muy interesante ver que aparece este operador sí, que está precisamente relacionado con las funciones eh, infrapolimonogénicas y que recién se definió y se demostró que está relacionado a estas hace algunos, como el 2020, creo, me parece 2022 por ahí. No tiene mucho que se definió este operador. Con ayuda de este lema y con ayuda de este otro lema, ¿no? En donde también hace falta encontrar esta transformada de Cauchy infrapolimonogénica, en donde nuevamente aparece este operador sí, pues podemos probar ahora nuestro tema 4, que es la solución al tema. Y como podemos ver, pues es bastante extensa, ¿no? Esta solución. Aparece aquí de orden K, aparece el patogénico, ¿no? Y aparece el operador sí que había comentado antes, ¿no? Que es este que está aquí. Y por supuesto, términos de frontera aquí auxiliares que surgen de los lemas. Entonces, en general, lo que hemos hecho es dadas las álgebras de Clifford que nos permiten de alguna manera factorizar el sistema de la Menavier, un sistema clásico de la teoría de la elasticidad lineal y que se estudia también aparte, pues, con teoría clásica de ecuaciones diferenciales parciales, con ayuda de las álgebras de Clifford, hemos factorizado este sistema. Esa factorización además nos permite iterar esa factorización, iterarla, pensar en un operador un poco más general, digamos, que es ese de aquí. Mediante este operador general, obtener fórmulas de representación explícitas para ese sistema iterado, y mediante esas fórmulas de representación resolvemos, perdón, un problema de tipo salto, ¿no? Un problema de salto que, por supuesto, eh, no es el único que podemos pensar, ¿no? Podemos pensar en otras condiciones de frontera, podemos pensar en otro tipo de problemas de frontera, no solamente de tipo salto, no solamente de tipo Riemann-Hilbert. Sería cuestión de pensar un poco qué otros problemas nos permiten resolver, ¿no? Porque también estas formas de representación, pues son solamente algunas, podemos pensar también en obtener algunas otras más. De manera general, esto es el trabajo que quería comenzarles el día de hoy. Gracias por su atención y bueno, cualquier pregunta, estamos aquí a la orden.
Muchas gracias, profesor Marcos. Gracias por su excelente presentación. Queda abierto el espacio a preguntas. Thank you very much, Professor Marcos. Now the space for questions is open. Feel free to ask them either in Spanish or in English. and we will try our best to translate them. Mientras surgen algunas otras preguntas, ¿qué tan importante consideras que es o cuál es el impacto que tiene la no conmutatividad en las álgebras de Clifford para esta clase de análisis? ¿Crees que lo complica demasiado o crees que es valioso por los resultados que se obtienen? ¿Cuál es tu opinión respecto a eso?
Ok, muy importante. Yo creo que ambas cosas, ¿no? En un principio, trabajar con álgebras no conmutativas, pues sí, suele ser pues en un principio desventaja, ¿no? En ese sentido. Te limita a ciertas cosas, te limita a teoría pues clásica, ¿no? Pero por otro lado, como mencionaba, pues a veces trabajar, por ejemplo, a ver, déjame buscar el sistema. Ajá, trabajar ese sistema de la Beer con teoría clásica, digamos, pues es una teoría ya muy desarrollada, ¿no? Sin embargo, trabajarlo desde esta perspectiva, ahora de la ecuación 3, pues te da otra visión, ¿no? De la ecuación, te permite estudiarla con teoría, eh, pues de las álgebras de Clifford, que te dan otra visión de eso, que te dan resultados que tal vez en teoría clásica no los puedes ver. Y creo que eso es algo muy rico, que toda vez que uno, digamos, encuentra, ¿no? Como que se puede decir, como que encuentra un cierto patrón en las ecuaciones, y encuentra un cierto patrón en las fórmulas que uno va obteniendo, como que eso en un principio pues pareciera muy complejo, ¿no? Ver, por ejemplo, el teorema 2, que es una solución un poco emborrosa, digamos de alguna manera, pero cuando tú ya te inmiscuyes en este tema, creo que ya lo ves como que un poco más simple, ¿no? Ves como que ese patrón de soluciones y te puedes ir como que en un aspecto un poco también incluso más algebraico, ¿no? Más sencillo de trabajar y que te permite resolver ese tipo de problemas desde un punto de vista analítico, claro, porque estamos en análisis, pero también una parte algebraica que te ayuda a obtener resultados muy bonitos, creo yo.
Ok, entendido, muchas gracias. En el chat preguntan que si tienen algún tipo de resultados computacionales para este problema.
Sería muy interesante, hasta ahorita no. Yo en particular no soy experto, digamos, en el tema de esto del análisis numérico, pero sería muy interesante aplicarlo, ¿no? Yo creo que ya teniendo las fórmulas de representación, se podría pensar en hacerlo y ver, ¿no? Sobre todo si estas fórmulas de representación son únicas, si tienen solución, perdón, ajá, si tienen solución única, o puede que haya algunas otras más, no lo sé. Sería muy interesante, pero hasta ahora no hemos hecho nada que tenga que ver con análisis numérico.
Ok, muchas gracias.
Sí.
Creo que ya no hay más preguntas. Muchas gracias, profesor Marcos, por su excelente presentación. Le agradecemos mucho haber participado en este evento. Esperamos que nos acompañe en próximos eventos de ICMAM. Se lo agradecemos. Muchas gracias.
Gracias por la invitación y gracias por el espacio. Saludos.
Saludos, feliz tarde. Okay,
Igualmente, hasta
everyone.
luego.
Okay. Okay, everyone. Thank you very much for attending the presentation of Professor Marcos from Mexico. Right now we have another half hour until the presentation of Professor Alessia Scanelli. Um, so we will meet at 20 Central European Time for the next presentation. Thank you.
Hello, everyone. Please, is Professor Alicia here? Professor Alicia, please, could you please share your screen with us?
One moment, please.
Could you please share your screen with us?
Yes.
Thank you.
Let me understand how can I do this one. This one, okay. Can you see it?
Yes, it's okay.
Perfect.
We have some few more minutes to the start of the presentation.
Okay, now you see the screen, but non-full screen, isn't it?
Yeah, the screen is okay.
But it is not a full screen like this.
It's not a full screen.
No, 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 no. But now you see the full screen.
No, your screen is off now. Your screen is off now.
Now it's full.
Yeah.
Okay. When I put the full screen, I lose the opportunity to see you in face, but no problem.
Yeah, but this one is okay.
Okay, so let me also open the video. Sorry, I forgot it. Yes. Okay, now you see me.
Yes.
Perfect.
Okay. So we are left with 5 more minutes to the start of the presentation. So yeah, I think it's okay.
Hello.
Professor Scanelli, how are you? Thank you very much for accepting the invitation of Frederick to this conference.
Thanks to you for inviting me to give a talk here.
Yeah, for us it's really a great pleasure to have you. And also this is a good opportunity for young researchers from Latin America and other parts of the world to interact with leading researchers in analysis and PD. So you see here.
I'm sorry because as I told you tomorrow and on Wednesday, I'm full and I have no time for the conferences, but today I had some time.
Thank you very much for joining us today. It's okay. We actually have, Erkin John also, Professor Erkin John Karimov, who actually was our first plenarist, is here. Thank you for connecting. Yes, it's very interesting for us to have both communities, ISAAC, the International Society for Analysis, Applications and Computations, and ICMAM Latin America, the International Community of Mathematicians from Latin America. So thank you. I will just a small comment. I will pass the chairing duties to Frederick Opoku from Ghana, from African Institute of Mathematics.
Yeah. So, Professor, once again, we thank you for honoring our invitation. So, Professor Alicia Karim is presenting on the title Evolution Descriptive Equation, Smoothing Effect Phenomenon. Prof, the floor is yours.
May I start?
Yes.
Okay, so let me first pass to the full screen. Like this. Okay?
No screen is showing.
You don't have the screen?
Yes.
What happens? Let me check. Let me Now you have the screen? Or not?
No, we are not getting a full screen, but I think this one is okay.
No, now it goes to full screen. One moment. I think that now you're seeing the full screen.
No screen is showing now.
No?
Yes.
What happens? Let me try again. So, full screen. Okay, let me try this way. And now I go here and there. And now what do you see?
Same as the old one. Yes, full screen now. Full screen now.
Okay. Now we are okay. So let me start. May I?
Yes.
Okay. So first of all, thank you very much for inviting me to this nice conference. I'm very happy to participate. Also here in Italy, it is now 8 o'clock. I suppose that on your side, you have sun and lunchtime, more or less. So let me immediately start with the conference. Thank you very much again for the kind invitation. I'm going to talk about some recent results obtained in collaboration with Alexandre Arias Jr. of the University of São Paulo in Brazil and Marco Cappiello of the University of Torino in Italy. The argument is, as you said, evolution dispersive equations, smoothing effect phenomena. The outline of the talk is the following. In the first part of the talk, I'm going to introduce the class of equations we deal with. This is the class of linear p-evolution equations, and I will give the definition of this class and also some examples of elements of the class. Then I will focus on the literature about the topic and give a first result concerning the smoothing effect for linear p-evolution equations. I will also try to give an idea of the proof, which will be the most technical part of the talk. In the second part of the talk, I will provide an application to nonlinear problems. So I will first introduce a class of nonlinear Cauchy problems I'm going to deal with, and then I will give a result about a local in time solution to nonlinear Cauchy problems. And then a very fast idea of the proof. I will conclude with some open problems and also work in progress. So let me define the class of equations we consider. We are going to consider the Cauchy problem Pu is f, u at the time 0 is g. Time is taken in a closed interval 0t, while the space variable is taken in R1, so monodimensional in space. The operator P has the following form. If we look at the operator, we immediately realize that there is one derivative in time facing p derivatives with respect to x. So this equation is non-isotropic because time and space have not the same weight. Assumptions on the coefficients. All the coefficients AP and AJ are assumed to be continuous functions of time. This means that we look for solutions in the classical sense, or at least in the weak sense, but not in the sense of Claudia Garetto's talk. Claudia considered the case of coefficients less than continuous, and so she worked in the framework of very weak solutions. In our case, the coefficients are continuous, so we look for solutions in the classical or in the weak sense. Other assumptions on the coefficients. Let me first focus on AP, which is the leading coefficient of the equation. This is assumed to be real valued. This assumption says that our operator is a so-called p-evolution operator with real characteristic. This class of operators have been introduced by Mizoate in 1961. And to realize that an operator is of p-evolution with real characteristics, you have to compute its principal symbol in the Petrovsky sense. That is, you substitute the operators with their dual variables, so dt becomes tau. And as for the space part, we take the leading term and substitute in the leading term the dual variable c to the operator dx. So we get a polynomial of order 1, tau plus apx to the power p, and if this polynomial admits a real root, then you are in the case of a p-evolution operator with real characteristics. Of course, in our case, the root of this polynomial of order 1 is tau equal to minus apx to the power p. Since we suppose ap to be real, we have real roots. Okay, so we are dealing with a class of anisotropic equations with real characteristics in this sense. The sense is that you assume you want to compare one derivative in time with p derivatives in x. In the particular case p equal to 1, then you have one derivative in time and one derivative in x, real roots, so hyperbolic problems. The class of p-evolution equations is so an extension of the class of hyperbolic equations to an anisotropic framework. And now let me pass to the coefficients of the lower order terms. These coefficients may depend also on space, and they are assumed to be with respect to space of class B infinity. This is the class of complex valued functions C infinity and bounded together with all their derivatives. In this talk, the lower order terms will have an important role, as we will see in the next slides. The positive integer p larger or equal than 2 is called the evolution degree of the equation. In the next slide, I will present some examples of operators arising from physics that are in the class we are considering now. The first and most well-known example is the Schrödinger operator. This corresponds to the case p equal to 2. The Schrödinger equation is the following. Here we see one derivative in time facing two derivatives in space. This is a real coefficient, so the degree of evolution is 2. And the operator admits a real characteristic given by a constant times c squared. Another very important example is the following, the Korteweg-de Vries equation. This equation describes the motion of waves in shallow water. And it is an example of an equation of degree of evolution 3. Indeed, if you look at the equation, you have on one hand one derivative in time, and on the other hand, three derivatives with respect to space, with here a real coefficient. This h is quite important, and it is the water level, which is assumed to be constant. Notice that this equation is nonlinear. Here we have a term u dx u. But as I said in the outline of the talk, we will give also results for nonlinear problems. But at the moment, let us think to the linear ones. Another example, again, of three evolution equation is given by the KdV-Burgers equation. This equation describes the flow of liquids containing gas bubbles, and it also describes the propagation of waves in an elastic tube containing a viscous fluid. The equation is the following, with some real coefficients AE. we have one derivative in time and three derivatives in x. Here is a real coefficient, so this is a three evolution operator. Notice that, as I underlined here in red, in this equation, a coefficient of order 1 appears, in the terms of order 1 appears, and this coefficient is purely imaginary. So it may happen also in physical examples that the coefficients are complex valued, as I assumed in the slide number 1. Another example, again for p equal to 3, another one of the several KdV type equations. This equation is again of 3 evolution and presents at level 1 a nonlinearity of type modulus of u squared. This equation is used to describe vortex filament dynamics in physics. And then, last but not least, the Kawar equation. This is an equation with evolution degree equal to 5. Indeed, as you can see, we have here one derivative in time and there 5 derivatives in space, with a real coefficient b larger than 0 in front of the 5th derivative. So this is again an equation of order 5 with real characteristic, and in this slide, we see several examples. All examples come from physics. Notice that the Schrödinger equation, as you know, is an equation that here is written in the monodimensional case, but it can be considered also in Rn, while all these other equations are typical equations with a monodimensional x. So, summing up, what do these examples say to us? The first information is that there are several equations coming from mathematical physics that are monodimensional. So we deal in this talk with monodimensional in space equations, of course, for simplicity's sake, but also because these equations have a physical interest. Moreover, we saw in the examples that complex coefficients may appear and lower order terms may appear in the applications. This means that it makes sense to consider equations with lower order terms. Moreover, degree of evolution P has a physical interest. We have examples for P equal to 2, 3, 5, and many others. Finally, all these examples are equations coming from physics with constant coefficients. Of course, in physics, you have to describe the reality, which is very complex, and usually in physics you take a physical quantity and you identify this quantity with, for instance, its mean value, because you have to simplify the equations to be able to treat and possibly to solve them. Only to give you an example, here H is the water level. The water level in shallow water is assumed to be constant, the average. But of course, all of us know that the water level is never constant. It depends on time and space. So for instance, if here you consider a water level that can change in time and space, we can treat the situation in a more precise way. This is the reason why we are interested in time and space depending coefficients and not only in constant ones. Okay, so we have focused the class of equations we would like to treat, and now let me give some literature about the topic. Well-posedness in Sobolev spaces for this class of equations. I will be fast in this slide because I suppose that everybody knows the concept of well-posedness. We say that the Cauchy problem is well-posed in the Sobolev space HS based on L2, if given right-hand side and initial datum in HS, there exists a unique solution, continuous in time and valued in the same HS, which satisfies an energy estimate of this form. We have that the norm of U in the Sobolev space HS is bounded by the norms of initial datum and right-hand side in the same space. Similarly, we say that the Cauchy problem is well posed in H infinity given by the intersection of all Sobolev spaces HS if there exists a positive constant delta such that for every right-hand side and initial datum in HS there exists a unique solution which is less regular than the datum. You see here S minus delta as the regularity of the solution. And moreover, in the energy estimate, we get that the norm of U in HS minus delta is bounded by the norms of G and F in HS. In this case, we have so that a phenomenon called loss of derivatives appears. While in the first case we found a solution in the same space as the Cauchy datum and right-hand side, in this case we find a less regular solution. We say that the solution has a finite loss of derivatives. But well-posedness still holds in H infinity because if G and F are in all Sobolev spaces, then also U is in all Sobolev spaces. So we can again obtain well-posedness in H infinity whenever we have a finite loss of derivatives. Literature about well-posedness in Sobolev spaces is very wide in the case of two evolution equations, that is Schrödinger type equations. Here I have written a list, non-exhaustive, of authors dealing with this topic. And I apologize for all the authors that I forgot. They are all here in the dots. And the literature is less wide for eigenevolution degree P. Indeed, there are some results by Arias Jr., myself, Chiara Boiti, Marco Cappiello, Massimo Cicognani, Ferruccio Colombini, Luisa Zanghirati, and other authors. What do we know from literature? The situation is the following. We know that whenever some of the lower order terms are complex valued, then you need some control on the imaginary parts if you want to obtain a well-posed Cauchy problem in L2 or in Sobolev spaces or in at least in H infinity. To understand why we need some control on the imaginary part of AJ, let me give an example concerning the case P equal to 2. If you deal with the 2 evolution equation, we have the T, a term of order 2, a lower order term of order 1, and then a term of order 0. If you want to prove well-posedness in Sobolev spaces, you have to provide an energy estimate. So let me try to obtain an energy estimate using the energy method, which states take the derivative in time of the norm of U squared, and if you find a suitable bound for this, then you get the energy estimate. The derivative of the norm of U squared is 2 times the real part of the derivative of U scalar U in L2. Now, the derivative of U can be obtained here from the equation. If we put an imaginary unit here, we get here the partial derivative, and here, there, and there, an imaginary unit appears. So we can write the derivative in time in function of P and of the coefficients. That is, we get the following. 2 times the real part of EPU scalar U minus this term, minus this term, and minus this term. What happens now? The first term, PU scalar U, can be, of course, bounded by the norm of PU squared plus the norm of U squared. this other term containing a2 and e the x square u is a purely imaginary term, so the real part vanishes. And then let us come to the pink term. This pink term has order 1, and we have two cases. If EA1 is purely imaginary, that is A1 is purely real, then this term vanishes. Otherwise, here, if A1 admits an imaginary part, a imaginary unit times A1 has a real part. And so we have here a real term of order 1 that survives. And in the case of a imaginary A1, this step is no more possible because we have an operator of order 1 applied to U that cannot be bounded by the norm of U in L2. So this last inequality holds only for imaginary part of A1 equal to 0. As for the last term, of course, we can take the supremum of A0 and get the norm of U squared. If you obtain an estimate of this type, then you can apply Gromval's lemma and obtain an energy estimate that is well-posedness in Sobolev spaces and in L2. But let me recall this again, all this computation work only if A1 has no imaginary part. Today, we are exactly assuming the opposite, that is A1 has an imaginary part. So if an imaginary part appears here, you have to manage it in some way. We need, as I wrote here at the beginning of the slides, a control on the imaginary part. If you can control in some sense this imaginary part, then this pink term will not destroy their well-posedness. Otherwise, you have no hope. So let me give some necessary conditions for well-posedness in H infinity of the Cauchy problem. First of all, in literature, we have a condition on the leading term AP. This term has to be an imaginary part which is non-strictly positive. This is a result by Mizoata. We are supposing today that this imaginary part is 0, so as for the leading term, we have no problems. And now, a condition on the subleading term. If you want to have some hope for well-posedness in H infinity, the term imaginary part of AP minus 1, as I said, has to be controlled in some sense. The control is given by this estimate, which has been proved by Cinosi in 1984 for two evolution equations, and by Boiti, Zanghirati, and myself in 2016 in the general case of p-evolution operators. Let me try to explain the necessary condition. This condition states that if you take the imaginary part of the subleading term and you integrate it in a neighborhood of a point x in Rn, then this integral in a neighborhood of x is bounded by a logarithm. To better understand the condition, let me test it. Consider, for instance, an operator of this form, where the subleading term is supposed to be constant. This cannot be allowed, because if you put here a constant, integration of a constant provides a positive power and not a logarithm. So you cannot allow for constant coefficients in the imaginary part. Another example. In this case, we have an operator of order 2 with a term here of order 1 given by an imaginary unit times a cosine. If you put here a cosine, the integration provides a sine, and the sine is bounded, so of course it is less than a logarithm. This means that as imaginary part of AP minus 1, you cannot allow constants, but you can allow, for instance, x-dependent coefficients having a bounded integral. And now, example number 3. Decaying subleading term. In this operator, we see that the subleading term is again purely imaginary and decays like x to the minus sigma for a positive number sigma. What kind of decay can we allow? Let me put this decay inside here. If the imaginary part is 1 over x, then the integral exactly provides a logarithm. If the imaginary part is 1 over x to a power larger than 1, then the integral is bounded. So we are okay for every sigma larger or equal than 1. But if here we put a power x to the minus sigma with sigma smaller than 1, then integration will provide a positive power, so no hope for well-posedness. Summing up, if we can allow here for decaying coefficients only if the decay is not too slow. Not too slow means decay larger or equal than 1. So in the talk of today, we will always assume here decaying coefficients with not too slow decay. What about sufficient conditions for well-posedness? Sufficient conditions are usually given by pointwise assumptions. These assumptions are the following. I'm not precise because I will be precise when stating the main theorem. Usually we have that there is a decay condition on the imaginary part of AP minus 1 with a decay larger or equal than 1. Otherwise, the necessary condition is not satisfied. And then for the lower order terms, we have similar conditions with different powers sigma j that are smaller and smaller and smaller as the order goes down. For instance, a typical sufficient condition has these powers sigma j given by j over p minus 1. These sigma j are 1 at level p minus 1 and 1 over p minus 1 at level 1. So they go down together with the order of the lower order terms. This is not enough again because unfortunately we need the decay condition on the imaginary part of the subleading term, decaying condition for the imaginary part of the other lower order terms, and also technical conditions on the derivatives. And on the derivatives, we need conditions both on the real and on the imaginary parts. In results of well-posedness in H infinity, the phenomenon of loss of derivatives that I described in the previous slide usually appears. But if you want to avoid this phenomenon, you have to ask for a large enough decay here that is sigma strictly larger than 1. And today we are going to consider exactly this case. Sigma is strictly larger than 1 because we want to prove a smoothing effect that is a better regularity for the solution with respect to the data. Of course, we have to avoid a loss of derivatives if we want to prove again. And now, let me pass to the other part of the literature concerning the smoothing effect for dispersive equations. Well, dispersive equations, that is, equations where we have a propagation speed which is different depending on the frequencies, enjoy these smoothing properties under suitable assumptions on the coefficients. Whenever an equation is dispersive, you have that the solution presents a gain of derivatives with respect to the initial datum. This gain is p minus 1/2, and a gain of derivatives with respect to f. This gain is given by p minus 1. This means that the solution presents a higher regularity, that is, it belongs to a Sobolev space of higher exponent. Let me be a little bit more precise, this is the literature about the topic. In the 80s and 90s, these authors, Konstantin Salt, Kennick, Pons Vega, Kato Sugimoto, and many others, started to prove the first results about a smoothing effect. And they considered homogeneous equations, that is, the right-hand side is 0, and the constant coefficients. Constant coefficients means that the imaginary part is 0, because we said that in the imaginary part, constant coefficients are not allowed. Then the case of inhomogeneous equations, so with an F on the right-hand side, has been considered by Kennick, Pons, and Vega. The introduction of X-dependent coefficients started in 2002 with a paper by Chiara, who considered the case P larger than 2, but for a particular class of equations. And then the case of Schrödinger type equations, P equal to 2, has been fully studied by Kennick, Pons, Rolvung, and Vega 2005, and Federico Staffilani in 2021. Finally, in 2025, X-dependent coefficients and 3 evolution equations have been considered by Federico and Tramontana. What do we want today? We want to extend this result to P evolution equations with arbitrary P. Let me also remark that an interesting consequence of the smoothing effect is the following. Whenever you find a smoothing effect for linear dispersive equations, then considering the associated nonlinear Cauchy problem, you can find the existence and uniqueness of a solution. This is the reason why I said at the beginning that I can treat nonlinear equations if I can treat linear equations. Whenever you can find a smoothing effect for the linear equation, you gain in some way a result of existence and uniqueness of solution to the corresponding nonlinear equations. Now, we are finally ready to give the main result of this talk. The result, to state the result, I need to introduce first the space where the solutions have to be settled. The space I want to introduce is the following: H, S1, S2. This is a Sobolev type space indexed by 2 parameters, S1 and S2. It consists of all the temperate distributions such that x to the power S2 dx to the power S1 u belong to L2, where this is an operator with pseudo-differential operator with symbol given by the product x to the power S2 and c to the power S1. This is the so-called Japanese bracket, which is equivalent to the modulus with the main characteristic that it never vanishes, and it is widely used in pseudo-differential calculus. These two indexes that describe the Sobolev cutoff spaces H, S1, S2 are related. S1 to the regularity of U. Indeed, if you put S2 equal to 0, you obtain usual Sobolev spaces. The index S2 rules the behavior at infinity of the solution. Indeed, suppose that S1 is 0. If S2 is positive, that is, U tolerates a positive power still remaining in L2, this means that this function or distribution U presents a decay. And if S2 is smaller than 0, then this U presents a growth as x goes to infinity. So Sobolev spaces with 2 indices may take care at the same time of regularity and the behavior as x goes to infinity. Okay, now let me go back to our Cauchy problem and to our operator, since they have been written several slides. Only in the first slides. So I recall that our Cauchy problem is this, and our operator is of order P with lower order terms. In the upcoming slide, I start with our main result. The result is the following. Consider the Cauchy problem. These two black assumptions are the ones of slide 1, continuous in time coefficients, leading term real valued, the other terms C infinity, bounded, and complex valued. I add here this pink assumption, which means that AP is not zero, never vanishes. It is larger than a positive constant. I can also assume that AP is always negative. This is the same. Let me assume it is always positive for simplicity's sake. And then this is the assumption on the imaginary part of the subleading term. This is exactly the assumption I stated in the previous slide. A constant, the imaginary part is bounded by a constant over a positive power with sigma larger than 1. As I said, the conditions on the coefficients have to be put on the subleading term, but also on the lower order terms. And so let me put conditions of decay which become less and less and less restrictive as the level of the terms go down. The correct power is J over P minus 1 at level J, that is 2 over P minus 1 at level 2, 1 over P minus 1 at level 1. As I said, this is not enough again because also technical conditions on the derivatives are needed to obtain a well-posed Cauchy problem in Sobolev spaces. So this is the really ugly list of conditions that have to be put on the derivatives. There are conditions both on the real and on the imaginary parts, and these conditions present a smaller decay with respect to the corresponding coefficient. So this is the set of decaying conditions on the coefficients of the operator. In the next slide, we have the results. First thesis of our paper. I try to explain the estimate which is written here. The thesis says, given m larger than 0, so u is in HM and positive, these are functions and not distributions. So given m non-negative, Cauchy datum G in HM, right-hand side F continues in time and valued in HM, there exists a unique solution, which is a gain of regularity HM and continues in time, such that this solution satisfies the following energy estimate. Colors help us to understand what happens in this energy estimate. Here on the right-hand side, we have the regularity of the datum and of the right-hand side, HM. The regularity of the solution is, of course, HM, but as you can see here, we can allow for a gain of P minus 1 half derivatives with respect to G and F, but this better regularity has to be paid by a growth at infinity for the solution. Remember that the first index rules the regularity and the second index rules the behavior at infinity. If here we have a negative index, then there is a growth in the solution. So if you want to find a solution with better regularity, you can have it, but you have to accept a growth for the solution. That is, you start with bounded in space Cauchy data and you obtain a solution with a possible growth at infinity. Moreover, you can also find the intermediate smoothing estimate. That is, if you accept a smaller gain in the regularity, then you have to pay a smaller growth as x goes to infinity. Second result of the same paper. What is the difference with respect to the previous one? The assumption on F. If F is continuous and valued in HM, we have this result. If F is L2 in time, but with a decay at infinity with respect to space, this is the index that rules the behavior at infinity, then if you ask to the function f to present a decay sigma half, you obtain that the solution presents a growth of type sigma alpha. In this case, the left-hand side of the energy estimate is the same, but in the right-hand side, we have here a difference. If you compare the space where F lives with the space where the solution lives, we see that with respect to F, we have that we start with a decaying F and we come to a solution U with the growth. We start with an F of regularity m minus p minus 1 over 2, and we get a solution with regularity m plus p minus 1 over 2. So we have a gain of p minus 1 derivatives from F to U. This gain is paid by a bad behavior at infinity. Starting with decaying coefficients, we come to a solution with a growth. In both cases, in the energy estimate, we have that the positive constant present here and there are bounded as t goes to 0. This is very important because we will apply this result to nonlinear equations, and we need to control these constants as t goes to 0, because we have to shrink time to obtain well-posedness results local in time. Now, some remarks and a comparison with the existing literature. What we have proved, roughly speaking, is that we can gain regularity with respect to the data and the right-hand side, paying some polynomial behavior at infinity. Moreover, notice that the weight in space, that is this sigma half, depends on the decay of the coefficients of the subleading term. So the subleading term rules the kind of decay behavior at infinity that the solution will have. Now, a comparison with the result of Chiara. As I said, Chiara considered a very particular class. Indeed, he considered a class where all the coefficients presented the same behavior, decay x to the minus sigma, with sigma larger than 1. This is a smaller class with respect to the one we consider today, and in particular, in our paper, we have different decay conditions on the coefficients, and only the decay condition on the imaginary part of AP minus 1 decides the behavior at infinity of the solution. The terms of order p minus 1, p minus 2, and down, 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 into, up to level 1 does not participate to the definition of the space where the solution lives. So we can better understand the behavior of the solution with respect to the behavior of the coefficients. Moreover, we give intermediate estimates about the gain of derivatives and polynomial decay. Indeed, in the paper of Chiara, these intermediate estimates were not present. And now we have the largest estimate, but also intermediate estimates for the solution. Moreover, with respect to the papers of Koenig, Pons, Rolvung, and Vega, and Federico Tramontana, we can treat every p larger or equal than 2, while that authors only considered the case p equal to 2 and p equal to 3. I have also to explain that, first of all, we treat only one space dimension, as I said at the beginning, and this is because our proof is based on a change of variable, which works at this moment only in dimension 1, while in the previous papers, x, the space variable x was in Rn. Moreover, in the papers by Koenig, Pons, and Vega and Federico Tramontana, the coefficient of the principal part is depending on x. In our case, it does not depend on x, but that authors had to put another condition on the coefficients, that is the so-called non-trapping condition. This condition is not present in our work because whenever the coefficients are, the coefficient AP is constant in space, then this condition is trivially satisfied. Otherwise, we would have put a more restricted condition also on AP. Now, an idea of the proof is the following. To prove the result, we change variable. We put v equal to e to the lambda v, u, where lambda is a pseudo-differential operator. To define the pseudo-differential operator, we give the symbol of the pseudo-differential operator. We construct it in such a way that it is invertible and provides an equivalent Cauchy problem, which has the same shape of the original one, but this new problem is well posed in L2 and in Sobolev spaces. What does it mean? As I described in one of the previous slides, the imaginary parts provide problems in the operator because in the energy estimate there are some real terms that survive. Okay, if you define in a suitable way this transformation, after the transformation you obtain an equation which is similar to the previous one, but in some sense the real terms at lower orders levels disappear. Disappear means that they can be bounded in some sense. And then when you find a solution V of the auxiliary problem, by inverting the operator, you can come back to the original function U solution of the Cauchy problem. The ideas behind the construction of lambda and the conjugation are the following. First of all, the transformation lambda is defined by giving the symbol. This symbol is the sum of p minus 1 terms. Each one of these terms is used to kill, in some sense, the real terms of level J. I only introduce the transformation and then I will skip some slides because time goes on and these are really technical. For instance, take the decay condition of level p minus 1. You can use this decay to construct the corresponding symbol lambda p minus 1. You integrate this decay after a separation in the phase space, and then you put a positive constant here to be chosen later on. What the introduction of this term provides. When you perform the conjugation with the operator e to the lambda, we have to conjugate all the terms of the operator P. In particular, when you conjugate the leading term, we have to perform a composition of 3 pseudo-differential operators. The rules of composition say that the symbol of the composition has a particular asymptotic development that can be computed explicitly, and the asymptotic development of the symbol of the composition turns out to be this one. That is, with respect to the original operator, we get a pixie to the power p plus a term of order p minus 1. This term of order p minus 1 presents the same decay as the coefficients of order 1, and it can be written in the following form. So, from the conjugation of the leading term, we obtain the leading term plus a term which has the same behavior of the imaginary part of a p minus 1 c to the p minus 1. And now, let me be fast. What happens? It happens that when you consider the real part of the symbol of the conjugated operator, we have both the imaginary part and this new term. This new term can control the imaginary part of level p minus 1. Indeed, by the equivalence between the modulus and the Japanese bracket, you can obtain this estimate. So we get a positive constant x to the minus sigma c to the power p minus 1. But if mp minus 1 is really large, then this quantity is positive and this symbol is non-negative. Now we can pass to operators level, and we have that whenever the symbol is non-negative, then the corresponding operator by Sharp-Gorning inequality can be splitted into a positive operator and a remainder that turns out to be of order p minus 2 with exactly the same decay as all the terms of order 2. Now, this positive operator disappears in the energy estimate, because in the energy estimate we have minus the real part, but the real part is non-negative, so with the minus it is non-positive and it disappears in the energy estimate. This term will provide the smoothing effect, and these are terms that allocate at lower order levels, satisfying the same assumptions. So this is exactly what happens. A term of order p minus 1 which disappears. This is the sense I was saying some slides before. You need suitable transformations such that terms of order p minus 1 disappear and these terms are gone. This term remains alive, but this term can be written as the norm in p minus 1 half minus sigma half. So this term provides the homogeneous smoothing effect. And in the energy estimate, also this term will appear, but this term will provide the inhomogeneous smoothing effect here below. And then the same can be done for the lower order terms, and the intermediate homogeneous smoothing effect appear. Now, let me pass to the nonlinear result. If we consider an equation PU equal to a polynomial, depending on U, the complex conjugate, and the first p minus 1 derivatives of U, and take a Cauchy datum G in the Schwarz space, with P an operator satisfying the assumptions of our linear problem, then we can find results of well-posedness also for nonlinear problems. In particular, this polynomial depending on all these quantities can be, without loss of generality, assumed to be a monomial of this shape. In this monomial, we assume that n plus r is larger than 1, that is, in the in this monomial, at least one term U or one derivative appears. We want to allow the case where only U bar is present here. Equations with right-hand sides of this form are really many, and in particular all the equations coming from physics that I discussed at the beginning of the talk belong to this class. For instance, KdV is U in facing dx, so n is 1, q is 0, r is 1. in this term, the same happens. Here we have a nonlinearity of type U squared, which means N is 1, Q is 1, and R is 1. And in the Kawara equation, U the XU, so 1, 0, and 1. We can allow for all this class of physical equations, but also many others, as is stated here in the right-hand side. The result is the following. If we consider the Cauchy problem under the assumptions of the linear smoothing theorem, and we take M and M tilde as in the definition here above, that is a positive M, large with respect to P, and also large with respect to N, where this N is such that given sigma larger than 1, the smallest even number larger or equal than sigma is 2n. So this is a even number larger than sigma, and M has to be larger than sigma in the following sense. M tilde is a real number belonging to this interval, so depends on M, P, and capital N. If M and M tilde are chosen in this way, then given a Cauchy datum in S, the Cauchy problem has a unique solution which belongs to the following space, the space of functions such that this norm is finite for some time t star small between 0 and t. What does this result say? Let me pass to the next slide where this inequality is rewritten. The result states that there is a unique solution for small time satisfying this inequality. So the solution is of Sobolev regularity and L infinity with respect to time, but it also presents a gain of regularity paid by a growth at infinity, and is also presents a smaller regularity and a decay at infinity, and all these quantities are bounded by a constant. This is the result which states existence of a unique solution in the space defined by this norm. The result extends the similar ones obtained for P equal to 2 and 3 in literature. And what is important to be noticed is that we have not only an extension to every degree of evolution, but also an improvement in the case of 2 and 3 evolution equations. Indeed, this sigma in our result is arbitrary and real, larger than 1, while in the previous paper this sigma is assumed to be an even integer. So we have also an improvement of that results. Now we are, I think I will skip the proof of the nonlinear result because I want in the last minutes to describe some open problems and work in progress. First of all, as I said, in our result, the leading term depends on time and not also on space. In the paper by Federico and Tramontana, 3 evolution equations, the dependence on X here is allowed, but the authors said we tried to extend to arbitrary P, but at the moment we didn't get the point, so we are not able to give this extension. Probably taking inspiration from their computation, it is possible to extend the presence of X in the leading term also for higher degree of evolutions, but at the moment we do not know how to do, and also Federico and Tramontana don't know how to do. Another interesting thing to do is to understand how the change of variable can work for X in Rn. At the moment, there is no guess about the extension to higher dimension in space. An interesting question is what happens in the degenerate case, because all these computations work when the leading term is strictly positive. But what happens if this term may vanish? Well, this is a work in progress. Together with Alexandre Arias Jr., we are studying also the case when AP may vanish in the case of three evolution equations. And finally, Eiger order with respect to the T equations are considered in a work in progress together with Arias and Cappiello. I think that my time is gone, so thank you very much for your attention.
Right, thank you, Professor, for this wonderful presentation. Now, it's time for questions. You can unmute yourself to ask questions or write in the chat box. I think there's one particular question in the chat box, so let me read it. Okay, so the question is, what if T goes to a constant? Can we recover the results for T, the constant? Slide 13.
Could you please repeat?
Okay, so the question is...
Is it in the chat, the question?
Yes, the question is in the chat. The question is in the chat.
New messages, let me...
Okay, T minus. Okay.
No.
So
How about having the result for early spaces, slide 15, this is the question?
Okay, the questions are two. We have one for slide 13.
This is the second one, this is the first. What if T goes to a constant? Can we recover the results for the T constant? Slide
T
13.
minus the constant.
If T goes to a constant, can we recover the results for T minus the constant? Slide 13, let me check. Slide 13. If T goes to a constant, I don't understand the question. If T goes to a constant, can we recover the results for T minus the constant? You mean if T goes to a constant instead of T goes to 0? And can we obtain results on the interval T0 capital T?
Yes, it seems that it is what is asking the participant, I think, because he said that yes.
T minus the constant, instead of having T that goes to 0, okay, yes. So, if T goes to 0, then okay, so now I understand the question. We are dealing with equations defined on the whole interval 0t, and the Cauchy data are given at the time 0. If you consider the Cauchy problem with in the interval capital T0, t instead of 0t, of course we obtain the same, because with the translation we can recover the case t equal to 0. And now, if this time, so on one hand, we can consider Cauchy problems on 0t or on T0t, which is indifferent. Because with the translation, we can come back to the case 0t. And of course, if t goes to a constant, we can obtain the same result, but what we cannot do is to apply the so-called bootstrap argument. In the hyperbolic equations, typically you say, okay, we have a solution which lives in an interval 0t. Now you restart with Cauchy data at the time t, and you get a solution existing in another interval of time. And then you restart with the Cauchy data at the lifespan of the solution and enlarge the lifespan by a bootstrap argument. This cannot be done in this class of equations because we have non-finite propagation speed. These are what is the right? These are anisotropic equations, and they do not have the finite speed of propagation, which allows the bootstrap argument. I hope I have answered to the question. It is yes, we can have t that goes to a constant, but you cannot bootstrap and fulfill the interval 0t by filling it in several steps. And then there was another question, one message. Okay. Oh, how about having the results for Orlist spaces? Slide 15. Slide 15, while the answer to this question is quite simple. Slide 15. Yes. We didn't try to obtain similar results in Orlist spaces. We only deal with Sobolev spaces for the moment. So we never tried. We are trying to obtain some results in Sobolev-Gevrey spaces, but not in Orlist space for the moment.
Okay. Professor Scanelli, I have a question, maybe related with I think it was slide 13. I think actually same slide that you show.
13, yes.
Yeah, here. Please, I don't know how to call these indices, right? That you have in the right-hand side, if are loss of regularity.
Sorry, please repeat, you don't know?
Yeah, I don't know how to call these indices that appear in the right-hand side, right? Loss of regularity or these quantities, but I would like to know about the sharpness of them, or if I could get intuition about from the information that allows you to get these indices.
You mean, for instance, here you have a decay. Here you have a growth at infinity. Is this growth sharp?
Right.
Okay. What we can prove is that we can obtain a solution which gains regularity, paying this with a possible growth at infinity. Indeed, go back to the definition of these spaces. In these spaces, we have that if S2 is positive, then U tolerates a positive weight still remaining in L2. This means that U has at least a decay x to the minus S2, but it may present also a larger decay. And in the case of a negative S2, that this is our case, if S2 is negative, this means that U tolerates a negative power, still remaining in L2, and this means that U may have a growth. That is, in the definition of these spaces, when S2 is positive, this means that you have a decay for sure, and this decay is x to the minus S2 or even better. But when S2 is negative, this means a possible growth. You don't prove that you for sure have a growth, only that this growth is possible. So here we are admitting a possible growth, and we don't know if this growth really exists and is exactly sigma alpha. At the moment we have no hints for the sharpness, while for the regularity, the same happens. That is, you know that you gain regularity, and you know that this is the result consistent with literature for the cases P equal to P equal to 3. We have that in the case P equal 1, there is no gain because in hyperbolic equations smoothing effect does not appear, but at the moment, as far as I know, there are no results about sharpness of these steps.
Thank you very much. And please, if I may, at the end, right, you mentioned that you are also taking a progress on Higger ordered,
Yes.
the Higger order case in time, right?
Yes.
Let's say just for the case of having the second order derivative in time.
Exactly. For instance, here you take the second derivative in time, and here we have, for instance, 2p derivatives in space.
Okay. And what kind of machinery are you going to use? Fourier integral operators or
Again, pseudo-differential operators. What you have to do is think, for instance, to hyperbolic equations of higher order. You factorize in terms of order 1 and then reduce to a first order system and provide a result of well-posedness. Here we can again factorize in terms which are not of order 1, but in terms of order 1 respect to t and p with respect to x. For instance, if you have 2 derivatives here and 2p derivatives with respect to x, you can factorize with 2 terms of this shape, and then by suitable reduction to a system, you can go back to a system of equations of this form. You can prove the well-posedness for the system and then go back to the original equation.
Thank you very much.
So the question is factorize in a suitable way the operator, reduce in a suitable way to a first order system, and then provide for the system a result of well-posedness. And after that, go back with the transformations.
Okay. Thank you very much. Thank you very much. I think, are there more questions for Professor Alessia Zanelli? Remember, you can write the question in the chat or you can raise your hand. I think it's not the case. I think our participants are very happy with your presentation. Thank you very much. So maybe,
thank you very much to you.
Thank you very much. Maybe a couple of announcements for tomorrow. For tomorrow, we are going to start with the plenary talk of Professor Elena Cordero at 14 in Central European Time. And please don't forget also that we are going to have in the second part of the program the plenary talk of Professor Anahit Galcian. So I encourage all of you to be connected tomorrow. And just an announcement that in our closing ceremony, we are going to announce a new arm of ICMAM Latin America, who actually wants to cooperate with mathematicians from Africa. And then we are going to have more information about this new project that we are going to call ICMAM Africa. So please, I invite you to connect. I invite you to connect to a closing ceremony if you are a mathematician from Africa, for instance, or if you want to have information about this project. I really encourage you to join us for this. Thank you very much, and then see you tomorrow with the talk of Professor Elena Cordero. Thank you very much.